My opinion from now, you can start.
Okay, thank you very much. Good afternoon, everybody, and welcome to this second day of FFP16 in the PER section. My name is David Sands. I'm chairing this session, and I shan't say too much more other than to introduce the first speaker of the afternoon, who is somebody whose work I've admired for a long time, and to anyone in physics education research, she needs no introduction. I'm talking about Paula Herron. Paula is professor of physics at the University of Washington and has done numerous things. I will just read some of them. She has given numerous talks at international meetings and science departments. She's co-founder and co-chair of the biannual Foundations and Frontiers in Physics Education Research Conference Series. She's held leadership roles in the American Physical Society, the American Association of Physics Teachers, and the European Physics Education Research Group, GIREP. She's served on the National Research Council Committee on the Status and Outlook for Undergraduate Physics Education, and co-chaired an APS-AAPT joint task force that produced the report Phys21, Preparing Physics Students for 21st Century Careers. She also serves as an associate editor of Physical Review, PER, which is perhaps something that she's best known for at the moment. She's a fellow of the APS, a co-recipient of the APS Education Award with colleagues Peter Schaffer and Lillian McDermott, and recipient of the Homer Dodge Citation for Outstanding Service to the AAPT. Dr. Herron is a co-author on the upcoming second edition of Tutorials in Introductory Physics, a set of influential instruction materials from Washington. So I'm not going to say any more other than to introduce you to Paula, and obviously there's no applause on a virtual conference like this, but very welcome, Paula, and I'll hand over to you without any further comment.
Thank you, David. Thank you for the lovely introduction. It's always a little self-conscious hearing people talking about me, so I'll just plunge right in. And I know that a few people who are. Can you see my screen?
Yes, that's fine. Okay.
I know that there are a few people who've heard me speak in the very recent past, and I apologize. I'm going to repeat a lot of what you've heard very recently, but I hope for the rest of you, there's something new. So anyhow, I'm going to be talking about conceptual understanding and reasoning ability. And based on the talks yesterday, which I enjoyed very much, I thought it would be good to start with the very big picture. And that is, what is physics education research? So I think everybody has a slightly different definition. I think of it as a field of scholarship that seeks to understand and affect how people learn, teach, participate, persist, and succeed in physics. Now, when I entered the field in 1995, in the United States, the intellectual domain, basically the ideas, the cognitive aspects of learning physics, were front and center. And there was very little attention being paid to the affective and personal domains or the social and cultural domains. Everything else that has to do with what it means to be in the physics community, to become a physicist, to learn physics, to apply physics in everyday life, and so forth. Now, those domains have greatly expanded. The field as a whole has expanded, so even the intellectual domain has expanded. But there's much more of an sort of an even-handedness among all of these intellectual, affective, and social domains. And moreover, we really are starting to pay attention to how interconnected all of these things are, rather than sort of disjointed or unconnected separate silos. We now understand how interconnected those are. It remains, however, that for me, the most interesting part is the intellectual domain. And in particular, my own goals are to model the development of expertise and to design instructional tools, strategies, materials, and environments that promote the development of expertise. So basically, myself and my colleagues and my students, we are trying to both come up with theoretical insights and practical advances in the physics teaching. So the studies I'm going to present here the data were mostly collected at the University of Washington in an introductory course for students who are pursuing the life and health sciences. At North Dakota State University, in an introductory physics course, primarily for students pursuing degrees in physics, engineering, computer science, et cetera. Essentially, all of the students who participated had taken physics in upper secondary school. So I'm just going to jump right in with the first example. And this is a question about sinking and floating. And again, I apologize if you've seen this multiple times over the years. It's just, I find it such a good example. It's so rich. Students are given, in the old days, students were given a sheet of paper with this drawing on it, and they were given some instructions. I've paraphrased here. They were told that there are 5 blocks of the same size but different mass, that each block, one at a time, will be released from rest in the middle of a tank of water. Think of like an aquarium, a fish tank, but the size. They'll be released from rest, and we show them where blocks 2 and blocks 5 will eventually be at rest, and we ask them to sketch the final positions of blocks 1, 3, and 4 and explain their reasoning. So what answer comes immediately to mind when you see this question? If you're like everybody else, probably the first thing you thought of was what we now call the descending line. The blocks are arranged from smallest to largest in terms of mass, and maybe they will end up 1, 2, 3, 4, 5 in this diagonal line. Now, if you thought about it for even more than a few seconds, you would realize that that seems probably a little bit suspicious. So you would have given it a little bit more thought. But very few of our students answer correctly. The first time we gave this, students had recently completed instruction on fluids in this introductory course. Only 10% of them gave a correct answer. So the correct answers we considered, the answers we considered correct were either to recognize that block 1 is slightly less dense than block 2, so it's going to be floating a little bit higher. We didn't care too much about the orientation of the block. The block 2 is approximately neutrally buoyant, so block 3 most likely is going to sink to the bottom. It's possible that block 3 is precisely neutrally buoyant and it remains where it's released, but block 4 will certainly sink to the bottom. So why do so many students answer this question incorrectly, even if they've been taught the relevant material? So we now understand, after decades of systematic research, that knowledge is developed through a process of construction, not transmission. So I think of this as sort of a small c constructivism, basically taking this idea that we all build our knowledge for ourselves. So the implications of this for teaching and learning are that students have constructed a lot of knowledge before they reach our classrooms, and that passive listening does not foster the reconstruction process. So if learning is a fundamentally active process, then listening is not going to cultivate that process. So I think of these 2 principles as the prior knowledge principle, that students have knowledge when they enter our classrooms, and the active learning principle, that they need to be actively engaged in order to construct or reconstruct new knowledge. In the United States, at least, in the field of physics education research and physics education more broadly, the active learning principle has gotten a lot more attention, and there's been a lot of development of active learning strategies for use in laboratories and small classes and large classes and remote learning and so forth. But it doesn't all respect the prior knowledge principle. So what's the problem with the prior knowledge principle? The challenge of prior knowledge is that what our students know or believe to be true when they enter our classrooms does not align well with the physics we want them to learn. And conceptual difficulties arise from attempts at reconciliation. And I'm going to illustrate what conceptual difficulties are. I'll just give you a couple of categories, but later on I'll try to flesh these out. So an example of conceptual difficulty is confusing related quantities, such as electric potential and electric field, failing to recognize the implications of the choice of system of interest. So answering one part of a question as if an object itself is a system, and another part of that same problem as if the system consists of the object and the earth. Relying on memorized results rather than deep principles, associating technical with everyday expressions, assuming inverse proportionality when it doesn't, when there's no reason to expect that things will be will change in a proportional way, overgeneralizing, invoking mistaken beliefs. This is the term that I'm using to express what is commonly known as a misconception. So a firmly held, well-articulated alternative belief that is at odds with what physicists believe. So the descending line, so when we go back and look at it, although almost all students drew this, this line and even expressed it verbally, their explanations were very diverse. There were lots of different things referred to in the explanations. Many of them contained incorrect statements about forces, buoyancy, pressure, and so forth. So our initial hypothesis was that the descending line response is a consequence of conceptual difficulties. In other words, that students have sensible ideas about sinking and floating, ideas that we could understand where they come from and can see that the sense to them. We can see that they would be reasonable things to think based on what they previously experienced. So they have sensible ideas about sinking and floating that are difficult to reconcile with what we're teaching. So there are two ways to that this hypothesis could play out, that we could test the adequacy of this hypothesis. One is, if it's true, the ideas that they're expressing should emerge in related situations. So it won't be strictly the 5 blocks question that students make the same incorrect statements about, say, pressure. It should also be true that if we attempt to modify how students are thinking by addressing those underlying difficulties, that is, if our interpretation is correct, then acting on that interpretation should improve student performance. So we're going to look at the related situations test first. So the related situation that we came up with is having 3 blocks instead of 5 blocks, 3 blocks of the same volume suspended in a tank of water. Well, we tell the students that blocks A and B are identical and have greater mass than block C, and also that blocks A and C are floating at are suspended at the same level. The students are asked to rank the buoyant forces exerted by the water on the 3 blocks and then to explain their reasoning. So hopefully, having learned about buoyancy, about Archimedes' principle and so forth, they'll recognize that because the blocks all have the same volume, they're completely submerged, they're displacing the same volume, and therefore the buoyant force on each of them must be the same. So the evidence supports this hypothesis. Only 20% of students gave a completely correct response when they were asked to rank these buoyant forces, and their explanations echoed those that we've seen in response to the 5 blocks. So for example, favoring specific cases of our broad principles. Some students said FB, the buoyant force, is equal to mg, thus A and B are equal, and since C has less mass, it has smaller buoyant force. So these are students are using an expression that is for the special case of something floating at rest in a fluid, and they're assuming that it's more general. Associating technical and everyday expressions. So some students said buoyancy can be looked at as the tendency for an object to be able to float. Since C has the lowest density, it will float the easiest. So that is an example of taking this everyday notion of buoyancy, how buoyant things are, and confusing that with the technical term of buoyant force. Confusing related quantities, this is a big one. The buoyant force on B is greatest because the pressure on B is greatest. We looked at many responses and interviewed students, and we concluded that students were not carefully distinguishing between the pressure and the buoyant force, and typically only thinking about the pressure on the bottom as being responsible for the buoyant force. Or the buoyant force on C is less than that of A and B, it displaces less water due to its smaller mass. This is a case of failing to distinguish between mass and volume. Now, we were very surprised when this came up among university students. It's well documented amongst primary school students and even younger children. And it was only about 10% of the students who expressed ideas like this. But this is a very serious conceptual difficulty, because if these students haven't really discriminated between mass and volume, everything we teach from this point onwards is not going to make any sense. They're not going to be able to truly make sense of what we're teaching them. So the hypothesis that the ascending line is a consequence of conceptual difficulties is supported because we did find that students had ideas about sinking and floating that were sensible, but difficult to reconcile with what we're teaching, and they emerged in related situations as well. They were not unique to the 5 blocks question. So the other side is trying to address the underlying difficulties and to see if that will improve performance. So the context for addressing underlying difficulties is a project that our group has been working on for many, many years, initiated by the late Lillian McDermott and Peter Schaefer in the very early 1990s. It is a set of instructional materials designed to supplement instruction in large introductory courses. So a typical format would be the students attend several lectures during the week. Then they may attend a laboratory experiment, but in a small group setting, they work through what we call a tutorial. So basically they have workbooks, and a few pages of those will be devoted to the most difficult topics in the course. And they will work on those in small groups. They'll sit around a table, they'll have their workbooks, they'll have some large sheets of paper, they may have some simple equipment, and the teaching assistants, who could be PhD students in physics education research or any area of physics, other instructors and so forth, will wander around the room, and they will periodically join a group, ask a few additional questions in addition to those that are contained in the workbooks, and try to help students go through the process of reasoning by themselves. So the tutorials are guided by many decades of experience in teaching, and they're also supported by theory. So one of the general principles is to teach by questioning, not by telling. This requires students to actually fill in all the gaps of the reasoning by themselves, not convince themselves that they're following an argument made by somebody else. They have to actually build the argument by responding to a series of questions. This also helps the instructors understand where, at what point the students are struggling, which parts they understand, and where they're unable to make a connection. These questions also help students become aware of their prior knowledge, aware of what they were currently thinking, what ideas they may need to rethink, and what ideas they can use as a basis for moving forward. Becoming aware of those is really important. We require discussions among students. We encourage exploration of phenomena, although these aren't labs. They don't do complicated quantitative experiments, but they do make simple observations intended to make the connections between phenomena and the formalism we use to describe it. And we employ specific strategies for specific challenges. So each tutorial is customized to the particular topic and the particular difficulties that arise with that topic. So I just want to say, during the COVID-19 pandemic, tutorials were conducted as Zoom breakout rooms. We made the decision when all instruction at our university went online for several terms. Rather than give up, we decided to assign students to breakout rooms in Zoom. The instructors, the TAs, and the professors joined these breakout rooms periodically. We couldn't use equipment, so we replaced the equipment with videos or simulations, or sometimes just directed students to pick up something in their dormitory room or their apartment or their home and try to do a simple experiment with that. And we have not done any comparative effectiveness studies because there are just so many different variables, and students were under such a situation of stress that we didn't think we would get valid results. So that was just an aside in case you're curious. So the tutorials on pressure and Archimedes principle and employ a number of specific strategies that match specific challenges. So one of the strategies that we use that we're sort of known for, and that are linked to theories of cognitive conflict and conceptual change, although we view them, we interpret them in a slightly different light, but elicit, confront, resolve. We start these tutorials by having students conduct experiments that help demonstrate the difference between mass and volume. So it's very much like old Piaget tasks, in which we give students objects of identical volume but different mass. We ask them to lower them into beakers filled to the same level of water. We ask them to predict how the water level rises will compare, and we help them recognize when they see that the water levels rise the same amount, despite the objects having different mass. We help them recognize that mass and volume are not the same thing. We operationally define concepts. So we define pressure in terms of force and area. The operational definition is really important for understanding whether or not you really understand how to measure a concept. We tend to view the definition of a concept as how would you measure that or determine its value. We guide systems to students to systematically construct concepts. So we go from Newton's laws, applying Newton's laws to volumes of water, to infer that there must be a linear pressure gradient, to inferring that linear pressure gradient gives rise to an upwards force on the fully submerged object that is depending only on the object's volume and the fluid's density. And this is pretty much the same argument that you would go through if you were teaching this, But the difference is we are getting the students to go through each step of the argument, each step of this derivation on their own. We also use a strategy that dates back to Arnold Ahrens that we refer to as idea first, name later, so that when you have a concept that seems to be useful, you understand how to measure it, you understand what it comes from, how it relates to other concepts, then you give it a name, rather than trying to use the name in place of what the concept means. In short, we're trying to help students develop a coherent conceptual framework for sinking and floating. So how do we assess our success in addressing these difficulties? So one way we do this is we give the same set of questions to two different classes of students at different points in instruction. So the reason we can do this is if we are, although there are many uncontrolled variables, the classical instruction experienced by both of these classes, that is lectures, textbook readings, traditional homework problems, that instruction may differ. It may have been delivered by different people at different times of day, even at different times of the year. The classes may be of different size. What we've learned is that as long as we're looking for instructionally significant effects, that most of those variables tend to be insignificant or to just wash out. So we can still derive conclusions from comparing different classes. So in this case, what happened is in the class represented by the upper horizontal bar, they had classical instruction. Then we gave them these questions, a 3 blocks question, a 5 blocks question. Then they participated in tutorials. The class represented by the lower horizontal bar, they had classical instruction, then they worked through the tutorials, and then they were given the 3 blocks and 5 blocks questions. So it's important to recognize that no student sees the same question twice. And those 3 blocks and 5 blocks questions are not explicitly part of the tutorials. So the evidence in this case partly supports our hypothesis, and I'll explain what that means. So the class that took the questions prior to the tutorial, very few students answered either the 3 blocks question or the 5 blocks question correctly. For those students who were given these questions after they'd worked through the tutorials, they did very well, or at least much better. They did very well on the 3 blocks question, with 80% of them answering correctly. 40% of them answered the 5 blocks question correctly, which is a significant improvement. However, it's not, it was still very unsatisfying to us to see that so few students were able to answer this question. So the reason I say this partly supports the hypothesis is that students did seem to have underlying conceptual difficulties. We were able to address those successfully, but it did not lead directly or necessarily to an improvement to solving the problem of the 5 blocks question. So many more students having resolved conceptual difficulties answered correctly, but it's still not an easy problem. So what I'm showing here is that they do have conceptual difficulties, but addressing those difficulties does not necessarily improve performance enough. So why do so many students continue to answer the 5 blocks question incorrectly, even after teaching that addresses conceptual difficulties? Well, one clue we see is in our own conclusion written to this paper almost 20 years ago. We wrote that on the 5 block problem, many of the written explanations lacked a logical link between the ideas expressed, whether correct or incorrect, and the predictions. In some cases, written statements appear to contradict the prediction. Moreover, essentially all of the incorrect ideas expressed were associated with the same prediction. It is possible that many explanations were attempts to justify a prediction based on intuition, rather than attempts to articulate a line of reasoning that leads to that prediction. So in short, it seemed to us that many of the students intuitively thought the descending line was correct. They wrote an explanation in which they cited some terms or expressions or relationships that they knew, and even if they didn't actually support their answer, that was their final response. So a few years ago, we became aware, my colleagues and I became aware of dual process theories of reasoning. And dual process theories of reasoning are the product of cognitive science and also have their roots in economics. They have their roots in people's attempt to understand why humans don't always behave rationally. So according to these dual process theories, and I should say it's a class of theories, there's not a single theory, there's a class of theories with a number of common elements. According to these theories, reasoning involves two qualitatively different processes. There's process one, sometimes known as the intuitive or heuristic process. It's automatic, fast, effortless, it always occurs. And process two, sometimes known as the reflective or the analytical process, that's deliberate, slow, effortful, and it might intervene if there's some dissatisfaction with the output of process one. In the literature, you'll find sometimes people referring to these as system one and system two, or type one processing and type two processing, but and many times those terms are used interchangeably for these sort of two broad classes of characteristic. There are a number of places to read about this. There's a really large literature. I would say if you're interested and you're hearing about it for the first time, that you might want to start with Daniel Kahneman's book called Thinking Fast and Slow. It's meant for a general audience, and it introduces the ideas both a historical perspective, and it's just a very engaging read. You might also check out an article that I wrote with two colleagues that was published in Physics Today about a year ago that attempts to interpret dual process theories for the physics audience. So an example, here's a question that's often cited as evidence of dual process theories. If it takes 5 minutes for 5 machines to produce 5 toys, how long would it take 100 machines to produce 100 toys? So before we get to talking about that question a little bit more, I want to introduce two more concepts. One is the concept of cognitive frugality. So this is the universal tendency to conserve cognitive resources. It's necessary. We really cannot devote the same effort to every task. We cannot devote the same level of analysis to every impression that's created by everything we see or hear or experience. However, we're not always that good at judging when that extra effort should be applied. So we're fallible in terms of correctly knowing when and when not to conserve those cognitive resources. In the literature, this is typically called cognitive miserliness, but we believe that frugality is a more positive term, that it just refers to this saving of resources for when it's really necessary. The other concept is cognitive reflection. So rejecting or delaying the acceptance of, at least, an easily obtained process one response requires cognitive reflection. So for the toys task, recognizing that it takes 5 minutes requires reflection on the output of process one, which is typically 100 minutes for most people. You know, you think 5 minutes, 5 machines, 5 toys, 100 machines, 100 toys, 100 minutes. Recognizing that that is incorrect and setting it aside, ignoring it while you work out what the correct answer is, takes reflection and engagement process two. So what does this have to do with answering a physics question? So in the article that I mentioned that my colleagues and I, Mila Krajewska and Andrew Heckler, wrote for Physics Today, we came up with this schematic for how reasoning with a physics task might be happening. So the purple box, we see a task is initiated. Say, for example, students are asked to answer the 5 blocks question. Based on their knowledge, their experiences, their expectations, process one will rapidly and involuntarily produce a provisional model. Sometimes in the case of 5 blocks, it is an answer unto itself. The path of cognitive frugality would see students saying, that seems fine, and writing that down as their conclusion. If they reflect on it and they go into this loop that involves analyses, which involves both processes 1 and 2, they may think about what they know, the formal relationships they know and have learned about sinking, floating, buoyancy, density, mass, volume, Newton's laws, etc. This is a path of sustained effort because it takes effort to do that thinking. Eventually, a model may be accepted after analysis and reflection, and that represents a conclusion. Several loops may happen, and as any representation, this misses out some key things, such as this is not really a linear process that takes place in this smooth loop. There is a lot of things happening almost simultaneously. So hazards that are encountered in following this path is that your intuition could pick up an irrelevant or an incomplete cue. It could look at the range of masses of the blocks and the positions of blocks 2 and 5 in the tank, pick that up, produce an incorrect provisional model, and then the first thing that comes to mind is something incorrect that you're either going to accept or that you're going to have to somehow ignore and set aside to think more carefully. Reflection may not happen. This response may seem so satisfactory that there is no need to think about it any further. You may actually reflect and undertake some analysis, but that analysis may be biased. It may be a process where you try to find justification for your intuitively felt response rather than trying to actually conduct formal analysis. You may simply not have the knowledge needed to answer it in the first place, in which case no amount of reflection analysis will lead to the correct answer. So what we refer to as an override error is a consequence of cognitive frugality. So even students who have adequate knowledge to answer correctly can sometimes fall into the trap in which process 1 provides an incorrect provisional model, and then insufficient reflection occurs, probably because the answer feels right, and so process 2 is not engaged. So it occurred to us at some point that the descending line might be an override error. That is, students assume that this floating at different levels is common, so that this descending line response feels right. When it comes to mind and they write it down, there are lots of other experiences that would tend to support that as being perfectly plausible. So we felt that what we needed to do is redesign the tutorials to reduce the plausibility of this intuitive response, not to address conceptual difficulties any more than we already had, but to simply help students get to the point that if that response occurred to them, it would not feel as right. It would feel, they would hesitate long enough to actually engage their analytical processes. So we revised the tutorials by adding some experiments. We challenged the plausibility of the common intuitive response by asking students to try to produce a neutrally buoyant glass test tube with a rubber stopper, and by adding some small grains, bigger than grains of sand, but very, very tiny pieces. They found that it was extremely difficult to do so. They almost always ended up with a test tube that would either float to the top or sink to the bottom. When they were finally able to achieve something floating, they found that by just adding one extra little grain or removing a grain would cause it to either sink or float. And so they could not achieve floating at different levels. So to test the hypothesis that this was an override error, what we did is we gave students the 5 blocks problem and some other questions, either after the original versions of the tutorial or this new version that had these new experiments. And what we found is the evidence supports our hypothesis, and I'll break that down. So the class that had the original tutorials, and I should say, I should mention this earlier, these results are from North Dakota State University. They were in a class that had physics and engineering students instead of the ones at the University of Washington, which had students in the life sciences and health sciences. So these students typically have stronger physics preparation. So these students, after the original tutorials, did 57% of them answer the 5 blocks question correctly, and 35% answered some quite difficult buoyancy questions that also required them to apply Newton's laws and so forth. The students at that university who'd had the new versions did much better on the 5 blocks question and exactly the same on the other buoyancy questions. So what we inferred from this is that the improvement on the 5 blocks is not due to improved conceptual understanding. It was improved because the modified tutorial helped students override the strong intuitive appeal of the descending line response. So I'm almost at the end here, so I'm going to wrap up and say that why do students make errors? This is a question that I find fascinating. Why, when students have been presented with carefully planned lessons carefully written textbooks, engaging examples, vibrant videos, simulations, compelling experiments. Why do they make errors and what can we do about it? Well, some errors result from the presence of imperfect ideas, not the absence of knowledge. But the imperfect ideas form the basis of new knowledge. We need to help students reconcile what we teach with what they already know or believe to be true. Other errors result from a failure to override intuition, not the inability to reason logically. But intuition is a valuable resource. None of us who are professional physicists could do anything without it, but we need to help students develop a healthy respect for it, not to simply accept it without question. And most of all, what we need to do is the different hazards represented by this graph need different instructional strategies. Where students are failing at different points, A, B, C, or D, we need to target what's going on there in order to help them learn. So I just want to acknowledge the work I've described is the collective work of many, many people. I want to especially thank Mackenzie Stetzer, Andrew Boudreau, Beth Lindsay, Mila Krajewskaya, my graduate students at the University of Washington, Anne Alessandrini and Kristen Keller, Peter Schaefer, Suzanne White, and many other members of the physics education group, past and present, and say thank you for your attention.
Thank you very much, Paula. So I'll quickly ask Alberto, who's our moderator, do we have any questions in the chat? I think we have a few minutes.
Good morning to all. Sorry for delay. Can I ask just a little question to you, Paula? I love so much the 5-block questions, and I use many times with my students obtaining results lower than you, 1%, 0%. Okay, you know my students are not very good students, but I want to ask this. Is possible that the 5-block question is not well formulated in the sense that he inducing the student the answer of the sequence. So it's not a problem of what they have in mind, but they immediately react and say, oh, it's suggested by the picture, no? But this is just a question that we can pose in any time. Are we sure that the questions effectively search a problem, a learning problem, or which kind of aspect search, investigate, no? And another aspect is of course, you have a request to student to motivate the wrong answer, the errors, no? It's possible that when we ask the student to motivate the incorrect answer, they reinforce the errors.
Yeah, okay, so the first one, yes, you know, it certainly seems like the arrangement of the blocks and the arrangement of the tank is just like perfectly set up for just the image to come to mind. I would argue, I'll say two things about that. One is if that's the case, and students then just, you know, say some stuff about buoyancy and they don't recognize that what they're saying is unrelated and doesn't support that answer, then it is still symptomatic of a lack of a coherent, a robust understanding of sinking and floating. The other thing I will say is we actually tried a different version, and this is written up in the paper, the physical review paper on this topic of rearranging things and trying to like just make it less visually appealing, and the results were really not significantly better. As far as your second question, the motivating, gosh, just give me another keyword.
If students motivate the errors, they reinforce. It's possible that.
Oh yes, yeah, that's quite possible. And this is what we think of it as a version of confirmation bias. So students have an answer, and then they want to support that answer by just saying some things that seem to relate to it. And it is quite possible that process creates, it sort of firms up that association. So we typically find that it's not enough to just get students to start thinking, but we need to actually support them to be critical of their answer and to say, not what do I know that would support this answer, but what do I know that might be able to criticize this answer. I didn't say that very articulately, but that we need to support them for looking for alternatives, not just looking for fragments of knowledge that would support what they already believe to be true. So it's sort of fundamentally a process of looking for alternatives and trying to find the flaws in their own reasoning.
Could I make a comment here, Paula?
Yes.
When I saw your talk at WCPE, which is on very similar stuff, and you mentioned that, I was struck by this question. I thought it was a brilliant question for illustrating dual process theory, but something else also occurred to me, and it's still there in the back of my mind, and that is the role of mental models. And I think I might have mentioned this at the time, but mental models, I've only just recently, in the past couple of years, got really deeply into the literature on mental models, and the work of Philipp Johnson-Laird, I think, is incredibly useful in this regard. And mental models show, or the theory of mental models explains the lack of logical thinking in a lot of circumstances, syllogisms and conditionals and whatever. And it struck me that one of the things that's not always explicitly mentioned in mental model theory, but I think is implied in a number of papers, but it seems to me the more and more I think about it, is the fact that when we form a mental model, we are triggered to establish a relationship. And so Alberto's question, I wouldn't say that that's an example of a poorly formed question, because any question could do the same. That image triggers that relationship, and that's what people act on. And like as in mental model theory, mental models really only contain the possibilities. They don't contain everything. And that's where the role of logic and reasoning comes in. It's in finding the counterfactuals, the things that will tell you the limitations of the mental model. And that's probably where the work should be, in stimulating this reflection on the limitations of our initial thoughts and our initial mental models. And I just wondered if you had any immediate thoughts. I see you nodding your head all the time.
Well, my initial thought is it's surprising to me that people have not developed links between the Johnson-Laird mental models and the dual process theories more closely, because I think they both are attempts to explain the same sort of things. Like, why would you answer a question in a way that is contrary to things that you know and believe and would answer, otherwise? Like, why would you do something that belies your own intelligence, knowledge, etc.? We have kind of, in our interpretation of dual process theories, we've kind of picked a few ideas. One is the provisional model is like Johnson-Laird's, the first available mental model. And I think a point of contact is this idea that once something seems good enough, it truncates the search for anything else. You don't think of all possibilities. A possibility comes to mind. Seems it satisfices. It's good enough, and it prevails, rather than being the result of deductive logic or careful analysis. But I do think there is a lot of room for seeing what is the overlap, what is the connections, what are the points of disagreement between those two schools of thought.
I know there's some other questions, but I'm conscious of time, so I think we ought to move on, otherwise we'll fall behind in the program. So
there is a question from Marisa.
I will recover if I can.
Can you be very brief, Marisa?
Yes, the question is, do you believe, Paula, that such a sort of work you have done in individuating the coherent path or paths in which students can activate in deep conceptual learning can be a research line? In other words, can we consider the planning of different kind of paths passing on the main difficulties as a way in which physics education research can contribute?
I hope so. You know, my colleagues and I we're trying to work out the details, like how to systematically, how could you systematically use this idea of the reasoning pathways to get insight into student thinking and to guide instructional improvements. And we're trying to come up with sort of some model or some examples of how that could be done. So I think the answer is yes, but we're still working out on exactly how to do that.
Many thanks.
Okay, thank
you.
So I'm going to close the discussion there because we do have to move on. Because
thank you, everybody.
Henaro is waiting in the wings, and thank you once again to Paula for a very interesting and stimulating talk. And so, if I can introduce Henaro Guisasola from University of the Basque Country, who is our next speaker. Henaro is assistant professor at the University of the Basque Country. He joined after graduating and spending some time as a teacher. I'm reading the introduction there and I haven't got my glasses on, which is a silly thing to do, so I do apologize. Between 2002 and 2012, he held the position of coordinator of the Educational Advisory Service of the University of the Basque Country, and he directed and developed the training program for university teachers in active teaching methodologies. Dr. Guisasola's research focuses on the investigation of student learning difficulties and their implications for the design, implementation, and the evaluation of teaching and learning sequences. He received the GIREP medal for the 50th anniversary in 2016, which recognized his leadership in the junior thematic group Physics Education Research at university and his efforts to introduce an active teaching methodology in undergraduate introductory physics courses. Since 2017, he's a member of the Committee of the Teaching of Physics of IUPAP and a member of the board of the Royal Spanish Society of Physics. So welcome, Henaro, and I pass it over to you without any more comment.
Well, do you see?
Yes, we can see that. Thank you very much.
A slide? Yeah.
Yes.
Okay. So, well, thanks, David, for your introduction. And hello, everybody. I want to thank the organizers, and in particular, Marisa Michelini, for the invitation to share some reflection about research in teaching learning sequence design from students' conception to design decisions. In my talk, okay. First, I will present a short presentation of research on students' conceptions. Afterwards, I will focus on the question, how can we use information about the students' conceptions in a way that informs more effective teaching? And finally, I will spend some time on the discussion and conclusions. Well, since the second half of 20th century, physics education has highlighted the importance of understanding students' ideas and students' conceptions. And today is widely accepted that prior knowledge can interfere with or facilitate new learning. There is a great deal of studies on students' ideas, and this research presents a broad range of descriptors. Maybe the first one and the most known is preconceptions, but there are another words like misconceptions, intuitive theories, blueprints, intuitive knowledge elements, and so on. So here I will use the term students' conceptions, many of which are do you hear me? Okay, many of which are considered alternative conceptions, and those that are inconsistent with canonical science. Oh my God, sorry, I have problems with the presentation. Okay, there is a great deal of studies from different countries, different period of times about students' conceptions. And this research, the first question that arose in this research was, to what extent are students' conceptions resistant to teaching? That is, the traditional teaching, the lectures can transform or can change the students' alternative ideas or no? Well, a lot of studies about this present evidence that well-organized lectures rarely work. Some students' conceptions resist traditional lectures. That means the traditional teaching is not very effective in changing students' previous conception or misconceptions. So the second question that arises is, well, we know that the students have alternative ideas, and we have to change or transform these ideas. So the question is, how can we use information about the students' conception in a way that informs more effective teaching? Or in a more specific way, how can curriculum designers' theoretical orientation about learning and the nature of science shape the approach to teaching? Well, here we have a lot of information from the literature. The literature tells us that the theoretical foundations influence both the analysis of students' conceptions and the teaching approach. I am going to analyze in detail this influence using example from our research, from the research of our group. First step in our research is to make explicit the vision of learning that we assume. In our case, we assume a social constructivism theory. The social means that we recognize the process of cognition is a process between the student or learners and its environment. In education, other students, teacher, textbook, and so on. And we complement this vision of learning with phenomenography. That is an empirical approach to determine the qualitative different ways in which individuals experience and understand aspect of the world or aspect of the curriculum. So from these general theories, it's clear that we have to take into account students' conceptions. And so we have to ask students about relevant or conceptual keys on the topic to be learned. At this point, we take into account another general theory, the epistemology of science, because literature tells us that conceptual keys arise in part from the knowledge of the epistemological and ontological problems that scientists had to overcome to construct the current theories. So we take into account not only some theories about the vision of learning, but also the epistemology of science. The research design on our students taking into account these general theories is the following. We define the teaching context. We take into account epistemological analysis of the topics. We define learning objectives. And then we ask students about ideas on this learning objective. So set up questionnaires and interview, administer them to students, and analyze the students' answer using phenomenography. To illustrate this process, I am going to show some examples from our research. A specific teaching context and topic is introductory physics courses at the university, first years of engineering, the second semester on electromagnetism. The specific topic is electric potential, capacitance, and capacitors. This topic lasts 2 weeks of teaching, and we have 4 groups at this level, and we ensure that the students have homogeneous knowledge. For this, we take into account the background, 3 semesters of physics in high school. Then they pass the exam to go to the university to the engineering degree, and there is a random distribution and so on. Well, with this teaching context, we make the epistemological analysis of the topic. In this case, we found 4 conceptual keys. The first one is about the process of charging a body. The scientific model for explaining this process needs 2 fundamental concepts: the concept of charge, the amount of charge, and the concept of electrical potential. From this model, we go to the definition of capacitance as a relation between the amount of charge and the electric potential of the body. And then to add some characteristic of this model, we take into account the role of the medium, the role of the closed bodies, and in particular, the capacitor system. And we can explain this system. Well, these are the conceptual keys that epistemological analysis tell us. And from these conceptual keys, we define learning objectives that students have to learn. For example, the first one that students have to understand: when a body is charged, it acquires electrical energy due to the work done by the battery or environment to charge it. Another one, the third one, the capacitance of a capacitor is the proportional constant between the amount of charge on the plates and the potential difference across the plates. So these learning objectives are based on the epistemological analysis. And after that, we are going to set up questionnaires and interviews to ask students. Let me show you one question of the questionnaire. This is the question 2. The objective is to inquire on students' ideas about the process of charging a body. The question presents two spheres, conductor sphere and another one, plastic sphere, dielectric sphere, and we connect each sphere to a battery. Students have to explain if the spheres will be charged or no, and describe the process of charging. Well, one example about interviews. We here have the type of interviews that we propose are probing, experimenting, and evaluating interview. That means students work in the lab with an experience, in this case, the Volta electrophore. And here students see an experiment with two plates, a dielectric plate and B conductor plate. And they use the Volta electrophore experiments to see and to prove with the neon tube if the B plate is charged or no. And they have to explain all the experiments in the different steps, 1, 2, 3, 4, and 5. So after ask to students, we analyze the answers. To analyze the answers, we use phenomenography rules. And the categories are defined in a bottom-up process from data. In this case, one research of the team analyze all the questions and propose the first categorization scheme. Then in the first meeting, all the research of the team analyze 20–30% of the question and discuss if the categories are well defined or we need to change these categories, taking into account the data. Well, finally, we define a categorization scheme and we analyze all the question. Well, from this process, in this example, we define 4 explanatory categories. You can see here in this table the categories and the characteristic of explanatory categories related to the learning objective. That is, the charging process, the role of potential difference or electrical potential of body, the environment, and the definition of capacitance. Here, for example, in the first, we call the first explanatory category amount of charge, because in all of these cases, students use only the concept of amount of charge to explain the processes and phenomena. For example, here, for the second question that I have shown, there is a transfer of electrons from the more charged body, in this case, the battery, to the less charged body, in this case, the sphere at the beginning, until the amount of charge is balanced. Then they use the same argumentation to explain why the metal conductor is charged and the dielectric no. It's the same there is not, they don't use the electric potential, and they usually confuse the amount of charge with the capacitance of a body. In the second explanatory category, students use the concept of force, electrical force, repulsion, and attraction between charges. For example, to explain the process of charge and the role of the electric potential, the battery performs the electrical force to bring the charges to the body. The body exerts a repulsive force, and it's become charged until it acquires charges. So here also they don't use the concept of electrical potential. Then sometimes when they define capacitance, they use the potential difference only in the equation, but without no meaning. This is very usual. This reasoning based on the equation is very usual in the third explanatory category. The students describe the capacitance and the definition of capacitance only using the equation, and only answer the question using the equation, and other qualitative question they don't answer. And finally, 15% of students, more or less, answer using scientific epistemic reasoning, and they use both the amount of charge and the potential difference between the battery and the sphere. So we define here 4 explanatory categories from a scientific model to scientific model. But we also specify the students' difficulties that have to learning objective. For example, here, we define the first difficulty related to the first learning objective. Students focus on the amount of charge of electric force in other model to explain the charging process of a body. They don't consider the concept of potential difference of the system or the electrical energy of the body. But we also define the gap between this difficulty and the learning objective. And to measure this gap, we use the didactical tool learning demand. Here, for example, in this first objective, we notice that the difficulty is a conceptual difficulty of understanding the concept. And if they don't use the concept, there is a high degree of inconsistency with the scientific model. But moreover, this difficulty is common not only in this topic, but also in the topic of electrostatic and the topic of electric current. So the degree of commonality is high. And this concept is connected with other concepts like electrical capacitance or like the potential difference in a circuit. So the degree of connectedness is also high. This is the reason because in this case, the learning demand is high. Another example for the second difficulty that appear when students use unscientific explicative categories students don't understand the concept of electrical capacitance as a relation between the amount of charge and the potential difference. So here we have a difficulty, a conceptual difficulty, but also an epistemological one, because students sometimes they use a reasoning base on the equation, or they use unscientific epistemic reasoning. This is the reason, because here the learning demand is conceptual and epistemological, and in this case also is high. Well, we can discuss with the other learning objective, and so we define not only explicative categories and students' difficulties, but also learning demands. So I think I have some examples about the influence of researchers' theoretical assumptions and analysis of students' conceptions. But what about design of teaching approach? Well, let me show one example with the same topic, electrical capacitance and capacitors. Here, from our vision of learning, we define explicative categories and learning demand. And this leads to structure our teaching learning sequence or our teaching material using problem-based structure. That means the teaching learning sequence includes general problems that guide students' learning. For example, to engage students in the interest of learning this topic. The first question is, what is the interest of storing charges in bodies? And here we present some problems related to engineering and to socio-technical problems. Or another problem that we present to students: what is the electrical capacitance of a body, and what systems allows us to store large amount of charge. But we set up a group of activities for each problem as scaffolding to help students in solving these problems. And in each set of activities, we use the strategy learning by inquiry with students. That means students have to make hypotheses, they have to justify their arguments using evidence. They analyze the result of the problem and so on. Well, let me show you one example about this type of teaching learning sequence. Well, we have here second activity for the problem, how is charge stored in a body? So here the problem is that the students have to explain the process of charging a body. This is the first learning objective. And we have a set of activities to develop, to solve this problem. One of them is the activity 2. In this activity, we have a conductor in the situation A that is not connected to the battery. and the total amount of charge is 0. In the situation B, the conductor is connected to the battery, and we can see that the current flows from the battery to the conductor, and we have evidence in the amperemeter. But in a short period of time, the conductor is charged and the current is stopped. The amperemeter tells us there is not current. So this is a problem that the students have to explain, but we propose some question as scaffolding. For example, if they have to explain that electrons or charges move, we warn students that remember how negative charge move in an electric field. And we know that students have a problem in using only the amount of charges. But so in the third question, we propose a question about electric potential. We introduce this concept, and they have to answer in relation to the charge and the electric potential. So we have more activities, 5 activities to solve the problem and to reach to a scientific model of explanation about the charging of a body. Let me show you another activity from another problem. Here the problem is, what is the electrical capacitance of a body? In solving this problem, students, with the help of teachers, have to reach to a qualitative and quantitative definition of capacitance. And here we have the first activity that introduces students to the problem and to the quantities that they have to use, they have to relate, and so on. What potential? Well, we have here one sphere with R radius, another bigger sphere than the first one with twice radius, and 2 spheres are connected to a battery. We know the potential difference of the first battery, and this problem is similar to other problems that they work in previous problems. And here also we have the big sphere with connected to the battery, and they have to make a hypothesis about what would be the potential difference of the second battery to get the same amount of charge in 2 spheres. And after that, we introduce the concept of a capacitance as a quantity for think about it. We don't introduce previously the equation of the capacitance. Here is only to propose hypotheses about the qualitative meaning of capacitance for the big and for the big and small sphere. Now we want the objective is that the students think about the amount of charge, the same amount of charge, the different potential difference of the battery, then they will work with the same potential difference and different charge and so on to introduce the concept as a qualitative way related charge and potential difference and define finally the equation of electrical capacitance. Well, then we implement this teaching learning sequence, we evaluate the result, we discuss the results and so on, but this is another story. In this talk, I want to point out the relation between the theoretical commitments and the influence on students' explanation and the design of teaching materials. So, some conclusions, some doubts, and some reflection. The first one, from our assumption of taking into account epistemological knowledge, we can define of this epistemological knowledge, tell us information about how to define learning objectives. From social constructivism and phenomenography, we obtain information to define learning demands. And from the explanatory categories and the learning demands, both, we have information to propose a teaching learning sequence, problem-based structure, with problem-based structure, with scaffolding, and with teaching strategies, learning by inquiry. This is examples about our research. And literature point out that making explicit the criteria of design decision is very important to share this approach and different proposals to the community. Moreover, we think different views of learning may produce similar results on research of students' conceptions. And we can see that in the literature. But rarely the teaching approach is similar. So we produce different teaching approach, and so we think we have to justify the design decision to the community. And in this way, the community will have the opportunity to compare and to see what is the better way for teaching, and what is the way of teaching that improves the traditional teaching. So, many thanks to Cristina Zuza, José Zubimendi, and Jaume Beller for the participation in this, in the example of this research. If you want to see all the research with results and with discussion about the teaching learning sequence, you can see that in different papers. And so, thanks you for your attention.
Thank you.
Well, I finish.
I don't see comment from other Paula. Okay.
Just clapping.
Paula?
Well, did everybody? I lost my mouse there. I couldn't find it, so I couldn't unmute myself. So
I had intended just to clap, but I will ask a question. So
Okay.
a very nice presentation. On your last slide, you mentioned that the different different people could find the same students' conceptions, but end up with very different teaching learning sequences. And how much of that do you think is due to differences in actual the learning goals as opposed to the theoretical framework or that is guiding the design?
Mm-hmm. Well, I think in the literature, using different vision of learning, for example, preconception, preprints, alternative frameworks, we get quite similar students' conceptions. I think until now, we don't think these students' conceptions are universal. Maybe we have to research more in different countries or in different period of times, but until now, I think we have a knowledge of students' conception that is quite homogeneous. But then the teaching materials, teaching learning sequence are quite different. For example, some teaching learning sequence focus on confronting students to alternative conception, on focus only on the conceptual difficulties. Others focus on students' resources. Others, like your presentation, in a very specific way of reasoning, the dual reasoning, and so I think this is good. It's not bad. I think it's good, but it's good if we explain to the community the specific design decision that we make in the process of the designing. And then, of course, but it's not the topic of the talk, but then, of course, we present the result of evaluation, the result of the redesign, and so on. And this on the other part. And the second part is that some of the teaching approaches are not really very different. When people explain strategies like learning by inquiry, problem-based learning, project-based learning, and so on, I think the strategies are very similar, and maybe the context is different. So I think in the future, we have to make explicit our decisions and our results, and then to find the similarities, to present more and more similar proposal for teaching. Well, it's more or less my idea. I don't know if I answered your question.
Yeah, yes, thank you, and I agree.
Thank you.
Okay, is Marisa, that is supported also by the Milan group. Please, Marisa.
Many thanks. So I reflect on the point that if you wanted to have interactive teacher learning activity, you need to produce the participation of students in any way. So I am thinking to what is the backward activity, just transforming your approach, research approach, in a behavior of teachers. For example, making a test at the beginning of each teaching learning session, using the answer for the work you are doing with students, and then to verify what is still open by means of test out. So this way of working, I try to apply during the teaching learning of primary teacher education, and it works very well. So in my experience, I spend one semester without and one semester using with the same student, the same teachers, this approach, just by means of a testing in which I individuate the learning notes, the problems, the points in which we can discuss together during learning activity, and the second one in which I don't use. And student express themselves as asking for test in and test out to be able to focus on the main aspect, otherwise are not activated the conceptual learning, they say. So maybe we can apply your research method as a behavior, as a research style, as a teaching style. Just a new method of teaching learning. And many thanks, Gennaro, for your contribution.
Yeah, thank you, Marisa.
Okay, so thank you very much, Marisa. Thank you, Alberto. I'm conscious of the time that we're supposed to be starting the next session after the short break. So as per yesterday, I propose that we should break. I think 5 minutes is too short to go make a cup of tea or do whatever you need to do. But let's meet back at 2. Well, in my case, 2:40. Your case, 15:40, or wherever you are. But 8 minutes, and we will resume for the next two talks. Thank you very much, everybody.
Thank you.
we're going to invite is Claudio Fazio, and if you just bear with me a minute, I would need to just find my words on Claudio. So very welcome, very big welcome to Claudio Fazio, who's an associate professor in physics education at the University of Palermo in Italy. He teaches physics education, history of physics to students in physics and general physics or physics education and prospective primary teachers. The member of the GIREP board, and his main research interests focus on the study of students' mental models, on PCK development in prospective teachers, and on the use of quantitative and qualitative analysis methods in physics and mathematics education research. So over to you, Claudio, and thank you for agreeing to give a talk at this conference.
Thank you very much, David, and I will share my screen. Put it in presentation mode. Okay, so in this talk, I will present some detail of the design and validation processes of a teaching learning sequence on surface phenomena. We will start have a look at an introduction dealing with the general aspects of the idea of a teaching learning sequence. Then we will discuss the theoretical framework and teaching approach that are commonly used in the design and implementation of teaching learning sequences. And then we will have a look to some detail of the specific teaching learning sequences I want to present you here, and of the related research. Then some results and conclusion will be drawn at the end. So science education research has been since a long time discussing the issues related to design, but also implementation and validation of topic-oriented educational pathways that are very well known as teaching learning sequences in the research literature. Typical characteristics of teaching learning sequences is their structure that is founded on research-based evolutionary processes aiming at making both the scientific and the learner perspectives interact in order to optimize the learning outcomes and their transferability to other contexts, learning contexts. So teaching learning sequences are often planned and used as both research tools to study efficacy of the activities and also the evaluation tools, and innovation proposals aimed at demonstrating how it is possible to tackle specific topic-related learning issues. In the last year, several theoretical framework and teaching approaches have been proposed for elaboration and improving of design and implementation of teaching learning sequences. Regarding theoretical frameworks, there are many. We can cite here educational reconstruction, engineering didactics, and so on, while the teaching approaches can be roughly divided in two, the traditional one that is teacher-centered, and another approach that is gaining a lot of popularity in the last decades, that is a student-centered approach related to the active learning environments. That can be described with different kinds of approaches, all related to the fact that the students are active part in the building of their knowledge. In our research, we decided to adopt the educational reconstruction theoretical framework, mainly because it fits well with our ideas, and the active learning approach that has shown to be effective in developing several aspects that we feel are relevant in education, such as improving student conceptual knowledge and understanding, modifying common sense conceptions, improving academic achievement also in relation to long-term retention of concept, development of self-esteem in students, but also in perception of efficacy in learning, and in improving critical reasoning skills and lines of reasoning aimed at both describing and explaining situations, and also in the understanding of science processes, and more broadly in understanding nature of science. In science education, active learning have been used to several aims, mainly to help students learning science by engaging them in activities that mimic the processes and procedures commonly used by scientists, but also to support and enhance student self-confidence, motivation, intellectual and emotional growth. There are obviously foundations of active learning. They can be traced in both learning theories, and the constructivist theory is obviously the first one to be taken into account, but also we have to take into account theories on learning styles and learner's mindset. And we start with the idea of learning styles that basically say that each person has one or more preferred ways to learn, and education must take this into account to improve learning. This kind of theory is sometimes confused with the theory, the well-known theory of multiple intelligence proposed by Gardner. They have both common aspects, but are quite different, if not for the fact that it is not so easy to identify different forms of intelligence, while it is quite easy to understand what are the learning styles preferred by students. Another theory that has been gaining popularity in the last year and is included in the theoretical framework of many approaches, like the well-known investigative science learning environment approach, is the theory of growth mindset, that basically says that learning is shaped by whether the person believes his intelligence is fixed or can be evolved. When persons believe they can get smarter, they understand that effort makes them stronger. And so a growth mindset prepares students to actively assume the responsibility of directing their learning, and encourages students to leave a sort of zone of comfort related to things that they know they can do well, but that is often unfruitful to produce appreciable cognitive growth. And we mean for cognitive growth the acquisition of skill comparable to those of an expert, a better appropriation of concepts and skill, development of self-confidence learning, and reflection on things one have learned, that is metacognition. The development of growth mindset can be empowered by deliberate practice that basically says that anyone can achieve excellent results with contextualized effort and practice that is practiced at increasing complexity level. So each student can become aware and reflect on personal learning styles, on the level of learning, and so develop new skills and cognitive functions. So let's have a look at our proposal of a teaching learning sequence on the surface phenomena. As we have seen, surface phenomena are very common in real life situations, but the approach that is traditionally used for its presentation at all levels of schooling very often complicates the presentation and explanation of the subject, and we have as a result students' low interest, incomplete understanding of the topic, and in general difficulty in appropriation of basic concepts. We have typical approaches to surface phenomena. First one, a macroscopic approach that is more common in the last year of high school and in the first years of university, that mainly describes surface phenomena as due to the action of forces on surfaces. a microscopic approach that is more common at university and deals with surface phenomena as due to interactions between molecules. And in the last year, an intermediate approach known as a mesoscopic approach has been described in the literature. In it, fluid is described as a set of n particles, Lagrangian particles. Attractive force and repulsive force are used to describe this interaction. This approach has gained some popularity in the last times, also because of the availability of computers also in high schools that can be used to implement this approach in computer simulations. Our research deals with the involvement of two groups of high school students in investigative activities on surface phenomena by focusing, as we said, on active learning, deliberate practice, adapted to different student learning styles to support learning, development of reasoning skills, and growth on mindset, and also perception of self-efficacy in learning. We basically had 38 12th grade students that we randomly divided in two groups. One performed a macroscopic approach and the other one a mesoscopic approach. Three researchers were involved in this work with two high school physics teachers that are teachers of these students. The activities took about 24 hours during this last academic year or school year, but obviously we had some problems in performing all what we want to do due to the COVID pandemic. Both groups reflect on the same topics, being involved in active learning activities based on the same observations and experiments, and on modeling activities, on small and great group discussions. But the difference between the two groups regards mainly the methods of analysis of the physical quantities to study. More specifically, group number one and group number two both perform qualitative and quantitative experiments by using an inquiry approach. But group number one performed analysis of the physical quantities using methods and tools supporting representation at a macroscopic level, while the students of the other group performed analysis of the physical quantities by using tools and methods supporting representations at a mesoscopic level, like videos and numeric simulation. The main goal is not to demonstrate what of the two approaches is better to improve learning in general, but instead to verify the aspect that each approach can show that can be considered relevant in promoting learning. And so, in order to obtain a final product that is a teaching learning sequences that should be trialed in the next academic year, that combines all the aspects that have proven to be significant in promoting student concept knowledge, intellectual growth, and the development of the right mindset. And the fact that we concentrate on these three aspects, let's explain slightly better what we mean for that. Student conceptual knowledge for us means better understanding of topics, evolution of common sense conceptions to scientific one, and long-time retention of the concepts students learn. Improvement of student intellectual growth means enhancement of interpersonal and social skills, the development of reasoning skills aimed at interpreting real-life situation and experiment, and a tendency to pursue further explanation also in contexts different from the context of the teaching learning sequence trial. And regarding development of the right mindset, we have the development of perception of self-efficacy in learning, obviously growth mindset, metacognition, and well-being in learning. We obviously, in our research, obviously all of these aspects deserve attention, but I will report here on some of these aspects due to time constraints, obviously. So let's have a look at the basic structure of the teaching learning sequence. Educational program, as I said, is composed by qualitative as well as quantitative experiments on modeling, on work performed individually by the students and the group discussions, and sharing in comparison of the results. All these activities are performed so that all the experiments and modeling activities are performed with increasing levels of complexity. Information is shared by the students, but also conveyed by the teachers by using several communication styles in order to fit the learning styles. Students are always asked to make previsions and make explicit their common sense knowledge and compare them with the experimental results. They are also invited to express their agreement with the group conclusion and to reflect on their perception of self-efficacy in understanding. Data have been collected by means on several methods. We have two questionnaires, one on general arguments on real-life situations not directly related to the things students do during the teaching learning sequence activities, and a questionnaire number 2 that is related to argument specific of the teaching learning sequences. These two questionnaires have been administered a first time before instruction, a second time after instruction, and will be re-administered 2 months after the end of the activities. That, in our case, is in about a week at the end of May. Then we also gave a satisfaction questionnaire on the teaching learning sequences, activities, and methodologies, obviously after instruction. And we also got data by means of student worksheet interviews to both students and the teachers, student logbooks, audio recordings of students' discussions and activities during the teaching learning sequence, and student scientific reports in their presentation to the general group. All in all, we have an IEL-like approach where students are actively involved in performing activities according to the active learning environment. We pay special attention to some aspects. In particular, students are asked to perform individual tasks before working in group, to reflect and express how much they agree with the conclusion reached in group, to build and to reflect and build on explanatory models as well as on descriptive models, to reflect on personal beliefs, achievement, creating and sharing scientific effort, and again reflect with the final group conclusion in order to understand if they really have understood the general construction of knowledge that is the final product of the activities. Let's have a look to some examples of the activities. We always start with the introductory videos coming from YouTube, in which students see some real-life situations, and then students are asked to perform qualitative experiments being given with some materials without any recipe of what they have to do, and they are asked to try and reproduce some aspects that they have found relevant in the movies they watched. Students are also involved in quantitative experiments built by using easily findable tools relating to measurement of surface tension, and all these activities are performed at an increasing complexity level and adapted to different learning styles, mainly in the way students can get information about the activities to perform. What, as we have said, differentiate the two groups are the modeling activities. Group 1, the one that was devoted to the microscopic approach, mainly do modeling by means of videos, PowerPoint presentations, graphs of forces acting at macro level, textbook review, and calculations, while group number 2 are more involved in simulations based on the implementation of an algorithm very common in the hydrodynamics, that is a smooth particle hydrodynamics, and student can actively modify some parameter of the simulation in order to see in real time the results of their modifications, like you see, for example, in these pictures related to capillarity. I show you also two movies of the simulations that the student obtain, in this case with the formation of a drop in presence of gravity and of interaction between the mesoscopic particles giving rise to surface tension. While in this other simulation, we have a drop of liquid that is made falling on a plate without the interactions that give rise to surface tension. In this other movie, you can see the formation of a drop of liquid in absence of gravity, but with interactions, obviously, between particles. And here students can also see in real time the visualization of forces acting on the particles of the simulation, so can have a direct graphical representation of what happens. Let's have a look also to the general structure of the student worksheet, that are the worksheets that students are given when perform the activities. I will show you some examples relative to the qualitative experiments. So with respect to watching and discussing video, students are requested to do single student prediction and small group prediction, and then perform watch the video, and then after the prediction, they are asked to reflect on that and see the movie and see if their prediction were in accordance with they've seen. At the end of the activity, note that the students are singularly asked to say if they agree with the conclusion reached by the group. The same is done with the design and performing of experiments related to the video. You see that the students are given with some materials, and the students are asked at first individually, then in group, to plan an experiment and then perform it and discuss about that. Evaluation. As I said, we have a lot of sources of information. Let's have a look at the questionnaires. As I said, we have two questionnaires. A first one made by 10 questions on general arguments, not directly related to the real life situations. And a questionnaire number 2 made by 11 questions, in this time specific of the teaching of the topics of the teaching learning sequences. You can see some example on the right. Both of these questionnaires were validated by using procedures commonly available in the literature. In particular, we concentrated on content validation and phase validation, as they are easy to do and particularly relevant. After the questionnaire were administered, the researchers, that is the 3 researchers and the 2 teachers that were actively involved in the teaching learning trial, sequence trial, found lists of typical student ways to answer the questions. These lists that were individual, so one for each of the 5 researchers, were then compared and contrasted during several meetings. And at the end, we obtained a shared list of typical answers. At the end of the discussions, each student also got an identification in terms of a binary array containing in each component the specific typical answers that he used to answer that specific question. This array can be used for further analysis. Let's have a look at some example of typical answers of one question of questionnaire 8 of questionnaire 1. Why is it preferable to use hot water to remove stains from the clothes? As you can see, we have here 6 typical answers, and we can see a sort of hierarchy in these kind of answers, but more of these in a few seconds. And here you have an example of a question, or questionnaire number 2. Do you think that it's possible to modify some water properties by adding soap? They actually did this experiment during the teaching learning sequence activities. Again, here we have 7 typical answers. In order to give sense of the typical student answers, we performed a phenomenographic analysis, because one of the main goals of the teaching learning sequences was to improve the student ability to develop reasoning skills aimed at interpreting real-life situations and experiments. And so 3, let's call them epistemological profiles, were identified also on the basis of previous literature results in terms of reasoning strategies students deploy when answering to the questions. These 3 profiles or categories are called practical, descriptive, and explicative, and we have here some description of it. Basically, we call a practical an answer that reflects the use of everyday context or other common life situations, similar to the one that is presented, to explain it. We call descriptive an answer where the student describes and characterizes the situation by trying to find in his memory variables and relationships that they think can be useful to perform let's call them an explanation, but this explanation is not based on a functioning model, while we call explicative an answer where the student proposes a model based on a cause-effect relationships or provides explanatory hypotheses introducing models that can be visualized at a theoretical level. And now let's see how we have categorized the different typical answers we have seen before. You can see that in case of question 8 or questionnaire number 1, the first 2 can be considered everyday type. The second one can be considered descriptive because it calls for a change in chemical composition, for example, something that they have studied in chemistry, while the last 3 questions can be considered explicative in the sense we have discussed before. And the same for question 10 or questionnaire 2. Again, we have an answer that is everyday type, 3, in this case, answers that can be considered descriptive, and the last 3 answers that are more explicative type. We will discuss here in some detail the results regarding the first analysis of answers to questionnaire 1 and 2 in the sense of the lines of reasoning, and we will also have a look at some preliminary analysis of some student logbooks, interviews, and scientific reports. So let's have a look at these histograms of the whole group of students, so group 1 plus group 2, before instruction and post-instruction. You can see, you can see here better that before instruction we had a lot of everyday answers, while after instruction there are still everyday type answers, but obviously at a lesser extent. There is a sharp decrease of not answered question, and in general we observe more descriptive and explicative type answers. In order to try to differentiate the 2 groups, we also I also show you the pre-instruction, post-instruction histograms for the 2 groups. Here we can say that both groups still give everyday type answers, obviously at a lesser extent, but some differences can be detected between the 2 groups. Group 1 highlights an increase of both descriptive and explicative type answers, but there is not a clear predominance of one of these 2 categories, while group 2 highlights a big increase of explicative type answers. Also, group 2 has only 4 questions not answered in the whole group. Let's have a look at the histograms related to questionnaire 2. Here we can immediately see that, unsurprisingly, we have more than 50% of not answered questions. Unsurprisingly, because the arguments dealt with in the questionnaire 2 are arguments typical of the teaching learning sequences, and very probably students did never hear about surface tension in the terms discussed during the activity. In post-instruction, we can see a sharp decrease of not answered questions. This is clear here. But also, it is also clear that we have more descriptive and explicative type answer, and the everyday type answers that are almost absent. Again, we have a comparison between the two groups. We can see that both groups show big degrees of not answered questions in both groups. And again, we see that we have an increase of both descriptive and explicative type answers in group 1, while have a big increase of explicative type answers in group 2. And explicative type answers are prevalent in group 2 again. I want to conclude this analysis with some preliminary study of the comments of students in logbooks and interviews, and some other qualitative data that can give us insight about the efficacy of these two approaches. For example, a student from group 2 say that it was very useful to have the possibility to modify the simulation parameter, as it allowed him to immediately see the way the liquid behaves as a consequence. A student of group 1 say that the video discussions graph on forces acting between a solid plate and water oil, he refers to an activity he actually performed, allowed him to see why water and oil behavior is different when placed on the plate. However, a student of group 2, and actually some students of group 2, found harder to explain experiments on capillarity than the ones regarding simpler situations like water drop behavior. And a student from group 1 says that he understands that cohesive and adhesive forces influence the liquid behavior, but he does not visualize their action well. And we have a general appreciation of the methodology used, with appreciation for the request of prediction and comparison that made students reflecting on what they knew and what they now know. An appreciation of the fact the experiments were not made in a demonstrative way, but only to explore in depth specific issues, and the possibility to plan experiments on the basis of observation made. Then let's have a look at some comments to students' scientific reports. We observed that students from group 1, the one devoted to the macroscopic approach, often manage to find in some way an explanation to the experimental results. And this happens both in simple situations, like in drop formation, and in more complex ones. Obviously, they cite forces acting on the surfaces, but when asked to clarify their answers, they do not always show a clear understanding of the way these forces act and their differences. On the other hand, the group 2 students are able to explain experimental results by making considerations and comments about interaction between particles. But this happens more in simple situations than in more complex situations, that are situations that involve interaction between solid and liquids. There are also some comments on students' participation, and I want to highlight here mainly comments made by the teachers that clearly evidence that the students of their groups highlighted a change in the way they participate to the school activities after the trialing. They frequently and spontaneously asked to prepare and conduct in-class activities by following the approach learned during the trialing. And then we have here some free comments of students that are interesting because they show the appreciation of the methodology. So, to conclude, we want to draw some preliminary conclusions. The two approaches have both points of strength and points of weakness. The mesoscopic approach seems to promote better thinking in terms of mechanism of functioning, that is particle interaction, while the macroscopic approach seems to facilitate more than the mesoscopic one the students to find a possible justification to experimental results, also in complicated situations, as we have seen. While group 2 students can explain simple situations by using, finding a functioning mechanism, but they find harder to give sense to more complex situations. All the students appreciated the investigative approach after some initial reluctance, and many students consider that this way to do physics is new for them and makes them feel more comfortable with the discipline than at school. So, obviously, more analysis is needed to allow us to fulfill our aims and design a new version of the teaching learning sequence. In particular, we want to perform also an analysis related of drawing profiles of each student and finding similarities between the way group of students behave with respect to the lines of reasoning they deploy when are asked to describe or explain the situation of the experiment. This will be done by means of cluster analysis. Also, a new analysis of the answers given by students in the second questionnaire is necessary in order to obtain information of improvements in contextual knowledge, and also this analysis will be performed in the re-administration of the second questionnaire that will happen in a week, I said you. So, in conclusion, I want to acknowledge the researchers and the teachers that participated in the trialing, and also I want to acknowledge the students of the two groups that were very active, if I can say that, in this trialing. And so, thank you for your attention.
Many thanks, Claudio. So, we have just a few minutes for some questions. So I'll hand over to Alberto, who's the moderator, to see if there is a question.
Valentina Bologna that asked which was teacher role during the activities done? Did they prepare materials? Did they manage lecturers?
Okay, the teachers participated in both the designing of the activities and also in the development of the activities. They took part not only as observers but as actors of the activities, and so they participated with several groups. They discussed with the student, assuming the role that the constructivist idea has for a teacher, that is to facilitate the construction of learning that should still be something personally made by students. And also the role was also to analyze together with the researchers the results of the trialing.
Okay, thank you. Well, if there's no more questions.
Thank you also from Valentina Bologna.
Thank you, Valentina.
Okay.
So there don't appear to be any more questions. Does anybody have a question before we move on? A quick one?
No more questions.
Okay, well, thank you once again, Claudio. And
thank you very much.
Thank you to
for
you.
a very interesting talk. And I'm going to move on now to our final talk in this session from Paul Logman, who is at the University of Leiden. Paul is he runs the bachelor lab courses.
There is a question. Sorry,
Ruben
Semperi.
Sorry, I just can we pick it up afterwards? Yeah, we'll pick it up afterwards. And, if you don't mind, Ruben, because I've moved on to Paul. We'll try and pick it up afterwards. If you could stay on the line, Claudio, we can pick up Ruben's question afterwards. But
Paul Logman is saying he cannot open video and mic. Maybe he wants to ask something.
Yes, I will ask.
Hi, Paul.
Organizer.
Hey, I'm okay now, but I couldn't talk.
Okay.
Okay, right. So yes, so Paul Logman runs the Physics Bachelor Lab courses at the Leiden Institute of Physics and is a teaching methodologist at the same university, in the Leiden University Graduate School of Teaching. So he received his PhD in 2014 for his research on students in reinventing the law of conservation of energy at the University of Amsterdam. And I sincerely hope it was the same law that everybody else understands. And he is now applying his knowledge of physics education research to both lab courses and his teacher training courses. So very welcome, Paul, and I will pass over to you without any further comment. So, Paul Logman, everybody.
I'm sorry, I have to get my presentation proper. Probably this one. I think you, what can you see? You have the full screen or the?
Yeah, I can see the full screen.
The full screen, no notes and everything.
No.
Okay, then I think it's fine. Thank you. Thank you to David and Marisa and the organizers for inviting me to talk. I expected, I have to show a little apology because of the connection I have. I'm on Wi-Fi, so I hope everything is good and understandable. And I expected to talk for a more physics audience than a physics education research audience, so I've made it a more general talk than specific physics education research talk. So I hope you don't mind. So as David explained, I'm the director of the Bachelor Labs in Physics at Leiden, and I'm a teaching methodologist. And I was hired to open up the experiments in Leiden. They were mostly cookbook experiments, and that's where I picked up and took my my experience in educational research, educational design research. So the outline of my talk will be the problems with those cookbook experiments and how to move forward. And I'll discuss some points that you might want to implement in your own lab courses. So I'll discuss those from an educational research perspective. Then I'll tell you something about possible quantitative research on lab courses and some qualitative research on lab courses. And I'll discuss the remaining problems that we face in Leiden at least, and probably other lab courses as well. So that's the outline of my talk. I'll try to keep it a bit short because I think we're running late. So the problem with cookbook experiments. Try this one. Here we go. Cookbook experiments are like exams. There's always a correct answer. And we teach students that there's always a correct answer by giving them cookbook experiments. And like Sergej said yesterday, students feel the need to prove the hypothesis. And I don't think that's the right idea of doing science research. You have a hypothesis and you don't mind if it's being wrong, because that teaches you just as much. There's also an even worse trend, in my opinion, that people use applets instead of lab courses. And applets do not offer a possibility to check your results with the real world, because the applet is made based on certain physics theoretical concepts, which may be correct, but always to a certain extent. So the only thing I would see there as a way forward would be students creating their own applet. I'm not going to discuss. So one of the points that Heather Lewandowski, who is the main quantitative researcher on lab courses, found is that if you focus your lab courses on concepts, the idea of students' beliefs about how experimental physics is done actually decrease by quite a bit, as you can see in the graph. If it focuses on both concepts and research skills, it still decreases a bit. And if you only focus on research skills, then the ideas and the real beliefs of students become more realistic. And this is compared to expert views. So this is quite an interesting comment on how to move, why to move away from cookbook experiments. What are the problems inside those cookbook experiments that make the problem in understanding how science works? So the thing with cookbook experiments is there's normally students don't build their own setups. They don't tweak it, they don't optimize it to get better results. They don't learn how to know what to do when they don't know what to do anymore. That's when you get stuck in your research and you have to think in different ways and in different directions. And also one of the main things with cookbook experiments is that the students don't need to come up with creative research questions. There's many more things that are problems with cookbook experiments. But that's, yeah, there's many more. So let me continue. Then there was a nice article, popular article by Natasha Holmes and Wieman, who wrote that we can do better. And I think we can do better in our universities. We should only use cookbook experiments when it's resolving some issue that we understand and that it really works. And if not, I think we should move away to move away from cookbook experiments and move towards more open experiments. And I'll show you how we did it in Leiden in a couple of minutes. There's more literature on that as well, on how to move away from cookbook experiments or how to convert cookbook labs into real inquiry labs, in which students really learn how to do scientific research. So there's a lot of literature, and one of the best things to start from is this Science Teacher article that you can see. So open research assignments, in this article I mentioned, open research assignments connect much better to students' abilities. They will choose an easy subject if they're not feeling very confident, but they will go into much more detail and much more theory if they're confident with the theory that's necessary for the experiment. And that way you can actually measure what students are capable of in terms of research, and especially in applying theory to research. So that's the direction that we went. And in the Netherlands, more general in the Netherlands, there are trends for most lab courses to move in this direction. There's a lot more collaboration lately, a lot of move towards more open inquiry. And the National Physics Practicals Days has been refounded, so there's a lot of interaction going on. Actually, there's been, because of this trend towards more open projects, there have been several publications by undergraduate students, so first, second, or third year students that publish in journals like American Journal of Physics, which is quite impressive in my opinion, physics education. And for these students, it's quite a feat. For them, it's an accomplishment that they wouldn't have expected to do in their bachelor's studies. We also wanted in the Leiden, especially a better connection to the research groups, so prepare them better for the research that they're going to do in the research groups. At the end of the bachelor, they have a research project in Leiden. So we want to prepare them for that as well. And there's a lot of activity going on in the Netherlands, at least from Delft and Leiden and some other universities that are trying to construct grading rubrics. And I'm taking away from Sergej's talk yesterday that the grading rubric from Eugenia at Kina's group is quite well developed, so we'll look into that one as well. There are more collaboration efforts going on, and I can tell you, I was a couple of weeks ago in London, where I met Michael Fox and Heather Lewandowski, who've joined up to start an international collaboration. Anybody that's interested can probably join us. There's also a European GIREP thematic group that's called Laboratory-Based Teaching Physics, which is run by Ian Bearden. Then there's the German collaboration, the DPG Schule in German, called Physics Lab Courses, which has also gone more international than only German, and the Dutch collaboration as the National Physics Lab meeting, as I discussed. And in the Netherlands, a Dutch grant has been granted to me and two colleagues of mine, one from Amsterdam and one from Eindhoven. And I'll tell you a bit more about that in the next slides, in which we are going to try to create open educational materials available for everyone, likely in English. So you're welcome to use it if you want or interested to look into it. We want to promote and investigate the nature of open inquiry labs, and we want to try and help other universities to move away from cookbook experiments and find a way of going towards more open inquiry. This is not limited to physics, it's also biomedical sciences and other biophysics labs that want to join in this cooperation grant. And we're very happy, of course, about having been given them. Now I will move into how we started in Leiden and the things that we took away from educational research literature and implemented it in our courses in Leiden. So we started thinking, we were two people at the time, and we started thinking, what do we want the students to learn? So we started back from scratch, even not taking into account anything that had already been written on the subject. We wanted to connect it to our bachelor projects at the end of the third year. So we just started thinking, what do they need to know after 3 years? So we wrote down about 130 learning objectives, which are, of course, way too many. And we wrote them down smart, which means they will become measurable. And then we grouped them. We grouped them per lab course and not so much as per practical or something like that, or per course. So we came up with these 5 steps within each research cycle, which is the measurement plan. We separated it from the analysis plan because there were a lot of difficulties in students writing their analysis before they start the experiment. Then do the measurements and get the results. Then analyze those results and then communicate it, in which we included presentations, reports, and everything. So we grouped all our learning objectives, which was quite easy to group them into these 5 categories. Felt quite natural. The next thing we did, and we reported this in GREP 2019, we tried to see whether it was connected to various other ideas about what students need to learn in bachelor labs, which means Dublin descriptors, which resulted in the Netherlands into the Dutch specific reference frame. I think every country has one. And we also checked whether they covered, Atkina's research abilities, and we saw that we could map them onto each other. So this picture is to show that. And I want to ask you, but you can't comment probably, but I would like to ask you if you agree with our final and main learning objective, which covers all those 5 subplots, that students are able to perform an 80-hour or whatever number of hours research project from first conception to presenting and reporting. So from getting their own first idea all the way up to reporting and sometimes even in a journal. I think that's the real thing, what scientists do. So they start from scratch from a research question and maybe build up on an old research and get from there and move all the way towards reporting the results. So you can find the article we wrote on the learning objectives under that link, under that name. One of the main things, main problems we have in Leiden is that we have quite theoretically primed physics students. And they are hard to engage in experiments. So They think experiments are not necessary. There's always a correct answer. Theory says it all. And why would you measure anything and check it? Theory is the basis of everything. And then they come into our lab, so we have to engage them. And there are a lot of literature about that. And I've taken out 7 points here, and you're welcome to send me an email if you want more information about the people I quoted. But I'll discuss a bit about how we implemented these ideas, how to engage students. And I'll end up later on in the talk to which extent this succeeded. So authentic challenges, as I explained, I think an authentic challenge would mean starting from scratch, think of your own research question, build your own setup, all the way up to reporting the results that result from your research. That's what we gave them, not all the time, but most of the experiments that students do here, at least 4 experiments in the first 2 years, are all completely open and maybe sometimes limited to a topic we want to address, to have the students address. You want assignments at their own level, and this happens with open experiments as well, because students will naturally choose a research question that they think they are capable of answering. We give them choices, or we give them the open research, so students become autonomous. They get the autonomy, the leadership of their own research, and this helps them motivate as well. And we, of course, create a supportive environment. We have about a TA in every 10 students that can help them at any time when they're in the lab. And even when they're preparing for the lab, they can ask questions to the TAs, teaching assistants. We make them collaborate with each other in pairs, but in the larger open projects, they also work in sort of research groups that are led by a specific TA who becomes sort of their professor. And we try to set it up to make it authentic as possible and have a real collaborative learning experience where everybody helps each other to find the answers, and also get students that have similar research in some respect and get them working together and help each other out. And the mastery mindset. So we want students not to bother about grades at the beginning too much. So the first experiments that they do, we do not grade. We just give them feedback on their lab journals and their articles and their preparations, but we don't grade them. And the final thing, we want the student to get the feeling that everything that they're doing is, there's a necessity to do so. And I think when you give them open assignments, but also more closed assignments, there should be a reason why students need to do what we ask them to do. Of course, in the open assignments, we don't ask them to do much, but in the closed assignments, we will. And I will tell you a bit about these closed assignments and open assignments and how they interact. Now, as I continue. So in literature, there are 2 well-described types of experiments, and the first one is the SQI by Holmes, structured quantitative inquiry. And the main things she puts in her description of that is that there should be some kind of repetition to, for example, improve your results. But repetition is more easily accessible in the ISLE experimental setup, which is much more open, and students learn general research skills. There's a natural repetition when students improve their setup, for example. There's natural research cycles within each cycle of research in which students continue and repeat certain stuff and get better at it. So what did we do with these 2 types of setups? So we used the SQI setups for students to learn some certain apparatus that we wanted to learn them, like an oscilloscope or function generator. If we wanted to teach them certain analysis skills, we gave them SQI assignments. And especially when students need to learn how to place certain new theory that they've just learned, and how to use that theory to base their research on. Of course, there's also general research skills that they learn during such experiments. The only thing that we gave in these experiments was the physics research. And we also connected that to research that's being done here at Leiden University, the physics department itself. So we always connected it to a certain group that's doing similar research or is using that part of research. So students could connect it to it being important for the university itself. And the second, the ISLE experiments we used for open experiments. And that was mostly to test whether they were capable of doing research on their own. So that's where we test the research skills. And in the SQI experiments, we do not test them that much, but we make sure that they learn the right apparatus skills and the right analysis skills that we want them to use later on in open experiments. Then there's also a problem when you ask students to come up with an experiment, is that they have to come up with some sort of question. They have a lot of difficulty doing that. So for example, this is an inspiration matrix, we call it. And on the top, there's all kinds of physics subjects, like oscillations, waves, patterns, and different kinds of waves, all kinds of things. And there's some physics content or analysis content or measurement content on the left. And students can just sort of throw a dart and think of something that has to do with the box they came in. Mind you, there's always etc. at the bottom and on the right of the tables or the matrices, because they don't have to stay within this matrix. So we always try to make them think outside the matrix. This really helped them, and normally we don't encounter much problems with students coming up with their own research question. We have this for every open course that we give. So we have this kind of matrix where they can sort of get new ideas or start looking on Google for ideas. And of course, they can stay outside the matrix as well, as long as we improve it. We do check their preparation. So how did we implement it? So we have 6 semesters in the bachelor, 3 years. So the semester 1 on the left and semester 2 on the left, then semester 3 and 4 in the middle, and semester 5 and 6 on the right. So in the first semester, they do 2 experiments, 1 closed and 1 open. This is generally the idea that we have. 1 closed to up their level of research skills, and then the second one to show off their level of research skills. So the first one is a closed experiment on electronics and superconductivity, and the second experiment is based on one of our research teams within Leiden, that's biological soft and complex systems. Then in the second semester, there's EN3 and EN4, which is again a couple. This is on oscillations and waves, and again a closed one and an open. And the same holds for optics, and then EN6, the final one for the first year, which students are doing now. That's why I'm in this small room on Wi-Fi and not in my own office, because that's too busy. And they can choose from electromagnetic, quantum mechanics, or optic experiments. In the second year, we start with 2 more closed SQIs. The first one in the third semester, which is about Fourier transform, phase and magnitude transfer functions, Bode plots. They learn how to do it and connect it to research that's being done in Leiden. And semester 4, we start with the second course on that, which is about signal processing, noise, and feedback. And again, that's a closed SQI setup. And then they're finalizing their projects with an open physics research question, where they can investigate anything that has to do with either feedback or noise reduction. They're really open in that. Then in the third year, in the 5th semester, they can have choose another a course, which is called experimental projects. That's completely open and is more based on teamwork, and working together and getting proper results. This lasts half a year, 1 day in a week. And they did LiDAR and last time they did delayed quantum erasers in groups of about 5, 6, maybe 7 students. And they really have to manage their own project and plan. Yeah, so there's a lot of project management teamwork going on there. And then in the 6th semester, they do the bachelor research project. That's not being done in the lab here itself, but it's done in the research groups with the different PIs all around the building. Again, the same picture, and now the apparatus that's being taught in the closed experiments, because there's no apparatus that needs to be taught in open experiments. So there's a digital multimeter and a MyDeck acquisition card that they learn in the first experiment, how to use it only. Then there's the function generator and the oscilloscope in the 3rd experiment. There's the optical setups that they have to learn in the 5th experiment. They learn how to use and program the MyDeck itself in the 2nd year, in the 1st semester, in the 3rd semester. And again, in the 2nd semester, they also learn how to use that better. The other ones don't have any apparatus skills that are specifically needed for us. And about their analysis skills and some theoretical skills that they need to use, error propagation and easy function fits are being done in the first one. And again, you see in the open experiments, no demands on that. Find peaks in like an oscillation, that damped oscillation, they will do in the 3rd experiment, and the 5th experiment they'll do some kind of intricate function fit, for example, the interference pattern of a double slit. Then in the 2nd year, I already told you, the Fourier transform, Bode plots, polar plots are the basis of the analysis that they use. And in the 2nd PE2, the 2nd practical in the second year, they do 2D Fourier transform, statistical analysis, noise analysis, and feedback. And again, the other open experiments don't have any demands. So how did it turn out in our labs? I'll show you a little bit about it. There's some experiments shown on the right side. And I'll talk to you a bit more about the picture on the bottom there. So of course, 1, 3, and 5 were the ones that needed most adaptations, and the other ones are just open assignments. So we just needed to create a matrix from which students could choose. And yeah, that's all they need. That's all we needed to tell them. So again, these are all coupled, and they're all connected to either courses or research teams within LIDA. Then I'll tell you, in the first year, 2 years ago in lockdown, one student, all the students had to do their optics experiments at home. So we gave them some material. No, we couldn't give them some material. They had to buy some material to create a double slit or some kind of spectroscopy, so grating, and they had to work on it at home. And during EN6 now, after that, they had to do some optics experiments, some other experiments at home. And now there's this guy, Lau Veenstra, student of ours, who built his own Michelson interferometer at home. A Mach-Zehnder interferometer at home. And he created it from Lego, the backs of iPhones and everything. So this was quite amazing, and we were impressed, and he wrote an article on physics education. Yeah, there was just an amazing guy, and we really separated the very good researchers, and he found out in his first year, to his amazement, that he was quite a good physics experimentalist. In second year, yeah. So I already told you we have 2 closed parts and 1 open part, and in the closed part, they do experiments of Fourier transforms, and in the open part now they have choices of anything almost in physics. And for example, we gave them this black picture, and we told them to inverse Fourier transform it, and then they found out there was a real picture in it. You couldn't see any information in the black picture. We have several of these black pictures, and students were just amazed how much they could do from that. The third year, on the left, you see the LiDAR, the setup that they made. So there's a mechanical setup and an optical setup up, in which they scan the room, one of our lab rooms. And on the right, this is the quantum delayed eraser, where 7 students built it all the way from scratch. and it's now in use in one of our research groups by one of the PIs. He has kept it because he needs it for his PhD students. So that was quite amazing as well. And I've asked them to write an article, but I don't think they have the time to invest. So, about quantitative educational research, there's several options that that you could use, but you need an instrument that's internationally used, internationally recognized. The main researchers in quantitative educational research on lab courses are Hedda Lewandowski, I have a link here to find her work, Natasha Holmes, another link, and Eugenia Atkina. And of course, we took a lot from them and tried to use it to compare our labs. It's something we want to do, and compare it internationally. And I think more people could join in when they start using the same measurement instruments. And the two measurement instruments that are easy and well established are the E-class by Hedda Lewandowski, which measures the ideas that students have on science research, compare it to expert views. And the other one is the scientific abilities rubric by the Atkina. These two things I think we can use for quantitative instruments. But my specialty is more in educational design research, which is qualitative work. The main paper on it, or it's actually a book by Plomp and Niveen, is very interesting to read, and how to make small cycles within your own course at your own university and still get results that you can build upon. So, for example, you need a design criteria to test it against something that you want to achieve with that design criterion. So, for example, we tried to add physics research questions and connect our research questions that we give to students to research within the Lyon. So that was our design criterion. We did it, and we wanted to achieve higher student appreciation because we wanted to engage students. And we actually did. So we did it in the second year, and the general appreciation of our courses went from 5.5 to 7.1. And for the second course, it went from 6.3 to 7.5. For the third course, which was already an open course before we changed it, it remained about the same. So for open courses, it's not a big enhancer when you change to physics research questions, but for our other, and connected to research within your institute, but for our other two courses, it really generated much larger appreciation of our courses. Also, the teachers were well appreciated. And you have to know that 7.5 is among the highest rated courses now, where we have students, we used to have students that were not very willing to join the lab courses. Now they are giving us a high appreciation, which is as high as the theoretical courses. The amount of students that passed was always the same. So if you want to go into educational design research, what can you use as a measurement instrument? What can you use to test whether you're reaching your goal? There are many, many things like the lab journals and particular articles and coded at some point. So it's like Claudio just told us, you can have the evaluation forms, which we use for our students. They always fill in an evaluation form at the end. The students' choices in certain apparatus, why did they choose that apparatus and not other ones? We give them lists of options to choose from. We collect those options, those choices, and see whether they are more creative or not. There's lots of things that you can do. But if you only do one measurement instrument, it's not really very certain that it's valid. So we always try to have one or two things that measure the same sort of thing. So it can, or we ask the students to confirm that what our idea is that we found, whether it's true in their mind as well. So this is the educational design research. So there's a lot of problems that we still have in the courses, of course, after a couple of years of renewing. But all courses that we have now implemented show that the students learn what we intended them to learn. But their choice in open practicals could be more diverse. So we're looking into these matrices and whether they are working as good as we wanted to. Students' study load is also very high. So they complain about that. So we need to find a way to make the study load for the students a bit less. This holds also for the second year. Study load is still a bit high. And again, the choice in open practicals could be more diverse, in our opinion. And year 3, it's another mandatory course. There's a competition with a lot of other courses, but about 15% of our students choose to do our course. So we would like to attract more students, but 15% is also a good group. They are really, really enthusiastic. So the remaining issues that we have is we want to implement and compare internationally. So we want to implement e-class and also a rubric that's internationally used. Students' preparations for lab have some problems. They normally don't go into the data analysis that much, and error propagation is almost never there, except in the second year it starts showing up. The students' workload, as I said, there's too many practicals per session, and there's a lot of things that we can improve, and we hope that working in research groups will help that as well. And then there's the rubrics. We have connected our own rubric because we had our own learning objectives. Now we have to see whether it connects to this Rutgers scientific abilities rubric. I'm quite sure because our learning objectives connected to Edkina's learning abilities, research abilities. So I think and I hope that this RSAR rubric will be very useful for us as well. I'm very happy if you have something to contribute to our ideas, or if you want to join in one of the projects I described earlier on. And I thank you for your attention. That was my talk.
Thank you, Paul.
Thank you very much, Paul. So I noticed one comment in the chat there.
From Laura.
Yes, from Laura. So I'll hand over to Alberto, and then
Laura. Oh, sorry. Laura.
I don't think Laura can talk, but I can read it now. So
someone is Dominique microphone. Hi, Paul. I missed the assessment rubric for physics inquiry. Not that long in the field, but Paul know the study. Not that long in the field, but
okay. I think this is Freek's rubric. That's one of the things I was telling you about, is that there's a lot of rubrics being built in the Netherlands. Freek is from Delft. And Freek, if you can confirm that the rubrics for physics inquiry is the one that you constructed. Yeah, okay. So I will look into it, and I have already downloaded the paper, but I haven't had the time during this busy year. So it's work for summer, and we will most certainly look into that. Oh, it's not Laura, but it's Freek on Laura's account. Yeah, please do, so other people can use it as well.
I don't see other questions.
No, there don't appear to be any other questions, but it was a very interesting talk. Thank you very much, Paul. Very, very interesting. I was going to ask what sort of level these experiments are at, but I saw from your talk later on that you have integrated this open inquiry at all levels of your undergraduate degree. Is that correct?
That's correct. In the first year, they do 3 closed and 3 open, followed by 3 open inquiries. And you have to know these are 4 afternoons or 4 mornings. So 4 times 4 hours. In the second year, they have they end with an 8 afternoons open inquiry, which they're finishing right now. And then in the third year, that not mandatory course, there they do half a year, so about 20-25 Fridays, and they can work all Friday on it. So that's a real big project. In the bachelor project, they have 24 EC projects. So almost the full 6th semester is one big project in a research group.
Right.
And we do get some results from research groups, especially from our excellent students. that they are quite impressed about what they can do. Sometimes they say they're even better than starting PhD students.
Well, I should think if you're publishing papers and you're managing to get students to publish papers from their work, that's really quite impressive.
Yeah. So one, Freek, who was in the chat, also published a paper, and there's also a paper from Amsterdam. And we're working on our second paper, which is quite interesting as well.
Right.
Capillary waves in water.
Okay. Well, thank you very much.
So maybe I can add some little thing, because we do differentiate these really good students, but I think everybody does that, but we can really identify them and give them the confidence of being an experimental physicist. Right. But we also cater for the lower achievers and make sure that they pass the course with good skills as well.
And are you confident that the lower achievers are developing at least critical thinking skills, that they're able to think critically about what they're doing and at least have an appreciation, a good appreciation of experimental physics and analysis of experimental data?
Well, they appreciate the courses more and more, as I showed. About their critical skills, it's the moment we made it more quantitative physics research. So we always ask them, which graph do you want to have at the end of your research? Which would be the resulting graph, and how would it look like? That makes them also the more critical, because now they have to find, okay, that's a graph, but in a graph I need error bars, and so they start thinking about how well their research will do, and some even start thinking about which apparatus they would choose instead of just grabbing apparatus that's available.
Okay, thank you. Well, there don't appear to be any more questions, and so I'm conscious that we've come to the end of this session, and somebody else.
We have just a question from Ruben Sampieri to Claudio Fazio.
He mentioned they'd already asked that question directly to Claudio in the chat. So
previous talk.
Yes, I did. Thank you very much.
Yes, we changed the ideas by chat.
Yeah, so I'll draw this session to a close, and thank you very much to all our speakers. I will hand over back to the organizers and enjoy the next session in, well, I think it'll be just under an hour, but so thank you very much.
Thank you.
Thank you very much.
Goodbye.
Goodbye. See you.
Is Professor Esposito ready to?
I am ready, Arisa.
Okay, so I don't see you now, I see you, I'm happy. So welcome to everybody to the session on history of physics. I have the pleasure to introduce Professor Salvatore Esposito. Salvatore Esposito is the president of the Italian Society of History of Physics and Astronomy, SISPA. He is considered one of the world experts about the life and the work of Ettore Majorana, whose unknown contribution he has put in evidence and published. Being a theoretical astroparticle physicist, he contributed to the neutrino physics and cosmology, in addition to relevant studies on several topics of applied physics. His work on the history of physics ranged from the modern physics to particular study concerning scientists of the 18th and 20th and 19th century. So many thanks, Professor Esposito, for your contribution, and please be ready to present your talk. Many thanks.
Thank you very much, Marisa, for your kind invitation and also for this very kind presentation of myself. Well, I start to, okay. Do you see the presentation?
Yes, yes.
Okay, thank you very much. My talk is about Ettore Majorana and his contributions to the science of the 20th century and even beyond. But who was Ettore Majorana? I think that the best way to introduce the character is probably to resort to the words of those who knew him closely. On Monday, 28 March 1938, at the Royal Institute of Physics in Rome, Enrico Fermi was in the laboratory with a student of his, Giuseppe Cocconi, when a phone call arrived from Naples. Fermi visibly blanched, so the young student asked him, "Professor, what happened?" Majorana disappeared. And Cocconi, who did not know Majorana, asked him naively, "Who is Majorana?" Years later, Cocconi still clearly remembered the answer he got from Fermi. You see, in the world there are various categories of scientists, people of secondary or tertiary standing, who do their best but do not go very far. There are also those of high standing who come to discoveries of great importance. And here Cocconi got the impression that Fermi put himself in this category. But then there are geniuses like Galileo and Newton. Well, Ettore was one of them. Majorana had what no one else in the world has. This seems a particularly exaggerated statement, especially for Fermi, who was certainly very balanced in his judgment. But let us start from the beginning with the family background. Majorana was born on the 5th of August 1906 in Catania, Sicily, to Fabio Majorana and Dorina Corso. He was the fourth of 5 sons. You see here his mother and 2 sisters. He had a rich scientific, technological, and political heritage. Just think that 3 of his uncles were chancellors of the University of Catania, members of the Italian Parliament. His father was only an engineer who founded the first telephone company in Sicily and then became chief inspector of the Ministry of Communication. His uncle Quirino Majorana was instead a renowned experimental physicist who was also president of the Italian Physical Society for many, many years. In 1921, his family moved to the capital, Rome, and later completed the last years of high school. Then he joined the Faculty of Engineering at the University of Rome, where he excelled. You can see here some of his closest friends and colleagues, Giovannino Gentile, Emilio Segre, Enrico Voltaire, Giovanni Enriquez, and so on. Now, in 1927, the director of the Institute of Physics in Rome, also Mario Corbino, launched a famous appeal to engineering students to suggest that the best ones accept the challenge of moving on to physics, where extraordinary opportunities were then opening up with the arrival of Fermi to the chair of theoretical physics, the first one established in Italy. Segre and then Edoardo Amaldi accepted the challenge. They also tried to convince Majorana to switch to physics as well. They succeeded, however, only to convince him to go to see Fermi to talk to him. Indeed, there was an exam to pass. Well, this first meeting was told to us by direct witnesses, that is Amaldi, Segre, and also Franco Rasetti, with almost identical and very enlightening detailed description. Let's follow here, for example, Amaldi's version. As you can see, Fermi was then working on the statistical model, later known as the Thomas Fermi model. The discussion with Majorana soon turned to the research taking place at the Institute, and Fermi gave a broad outline of the model and showed Majorana reprints of his recent works on the subject, in particular, the table showing the numerical values of the so-called Fermi universal potential. Majorana listened with interest and, after having asked for some explanations, left without giving any indication of his thoughts or intentions. The next day, towards the end of the morning, he again came into Fermi's office and asked him, without morado, is a true disgrace, we can see, to show him the table which he had seen for a few moments the day before. Holding this table in his hand, he took from his pocket a piece of paper on which he had worked out a similar table at Tom in the last 24 years or even less, transforming, as far as Segre remembers, the second-order Thomas Fermi nonlinear differential equation into a Riccati equation, which he had then integrated numerically. He compared the two tables and, having noted that they agreed, said that Fermi's table was correct. He then went out of the office and left the institute. A few days later, he switched over to physics and began to attend the institute regularly. Evidently, Fermi had passed the exam. And then Majorana, reassured by the fact that good things were being done there, finally decided to move on to physics. Well, this seems just an amusing anecdote, likely somewhat exaggerated by his friends in their recollections. But interestingly enough, several years ago, I did succeed to reconstruct what Majorana effectively did in that night, since the whole calculations were reported by Majorana in his personal notebooks, now kept in Pisa. We published them some years ago. You see here just the first page of those calculations. Well, in those few hours, Majorana first transformed the Thomas Fermi equation into an Abel equation rather than a Riccati one. But here we can certainly excuse Segre for his inaccuracy. Indeed, Abel's equation is a generalization of the Riccati equation. But surprisingly, he did not solve such equation. It said just to prove the existence and uniqueness of its solution. Note that the corresponding theorem was proved by mathematicians only in 1934, while no analytic solution of the Thomas Fermi equation was known. Then Majorana came back to the original Thomas Fermi equation and transformed it into another first-order differential equation, which is solved by a series in terms of only one quadrature. And from such a solution, he finally obtained the table of numerical values mentioned in the account before. You can see it here. I note that according to what is known, the scholar Thomas, the Scottish Thomas, worked for about 1 month to obtain the approximate numerical solution of his equation. Fermi took about 1 week. Indeed, his formulation is cleverer. And Majorana just a few hours. But just a few hours to find the analytic solution from which to derive the numerical values. Perhaps Fermi hadn't exaggerated in describing Majorana to Pocconi, but let's go on. Majorana joined the Fermi group and did make a substantial contribution to it, starting from a few months after the event just told, when he published, while still undergraduate, his first paper in collaboration with his friend Giovannino Gentili. We will come back soon. In December of that same year, he was also invited by Fermi to give a talk at the general meeting of the Italian Physical Society, SIF, on some applications of the Thomas Fermi model, again reported in these notebooks. And then he finally graduated in July 1929 with a dissertation on the quantum theory of radioactive nuclei. Note that this is the first paper on nuclear physics in Italy. The articles published by Majorana account to just 9, plus 1 posthumously published in 1942 by Gentile. Each of them, however, remarkably, is a small or large masterpiece. Let's take a quick browse to try and appreciate something about them. Well, the paper number 1 on the splitting on the ring and optical terms caused by the spinning electron and on the intensity of the cesium line is the only paper written in collaboration. It contains probably the very first application of the Dirac equation. The Dirac paper appeared indeed just a few months earlier, which the authors exploit to deduce correction to the Fermi universal potential. When their prediction compared with the current experimental results, the agreement is within 5%. Probably not a very striking result, but note that a better approximation came only in 1997. The paper number 2 is about molecular spectroscopy and concerns the formation of the helium molecular ion. It introduced a generalization of the Heitler-London method inspired by group theory, a topic particularly liked by Majorana, who was among the 3 or 4 physicists in the world at that time to use it. The same quantitative results were qualitative results were obtained independently a few months after by Linus Pauling, while we have to wait for 2 more years for the same quantitative results. Here you can see, just a joke. This small star here also in the following slides, denotes a Nobel laureate, Linus Pauling, was indeed Nobel laureate. This is just a joke. Instead, it is interesting to note that Majorana predictions are now in better agreement with the experiments than current theoretical estimates. Go on. Paper number 3 on the presumed anomalous terms of helium is again on atomic spectroscopy. This was the dominant activity of the Fermi group in those years. And again, Majorana employed group and symmetry arguments to obtain predictions confirmed only in 1994. The same results were rediscovered some years later by Tayo Vubius. Here, a student of Samuel Goldsmith, who, however, did not employ symmetry properties, so that he initially made a mistake about spectroscopic assignment, which was corrected only 10 years later. The paper number 4, regarding a pseudopolar reaction of hydrogen atoms, contains, in some sense, a revolutionary realization of the Heitler-London theory. Why revolution? Since Majorana introduced ionic structures in homopolar bonds to apparently conflicting concept, ionic bond versus covalent bond. Only decades later, the same was started to do for artifact eigenfunctions, and such ionic structures are now known as Majorana structures. They were first acknowledged by chemical physicists in 2006, the year the centenary of the birth of Majorana. Those scientists indeed participated to a famous conference in Catania. He participated, and there they discovered what Majorana did. The paper number 5 on the theory of incomplete P-prime triplets introduced what Majorana termed spontaneous ionization, later known as auto-ionization according to the American Sheston. That is the possibility of a process taking place in the optical range that is completely equivalent to the Auger effect already known in X-ray emission. The generalization of the existing Wenzel theory allowed Majorana to make prediction about controversial levels that were experimentally identified only in 1955, while the complete validation theory came even later, 1970. Here, however, the interesting thing is that Majorana did not publish all his work on the subject. In particular, as we will see, he introduced the so-called quasi-stationary states, that is a mixing between a discrete level and a continuum, not only in atomic physics, and this was officially done by Ugo Fano in 1935, while some results were later discovered only in 1961, but also introduced in the theory of nuclear reactions with what should be termed Majorana-Fano-Feshbach resonances rather than only Fano-Feshbach resonances. Similar phenomena have been very recently discovered also in high critical temperature superconductivity, in ultra-cold gases, and so on. The paper number 6 about oriented atoms in a variable magnetic field is a real gem, with a number of both physical and mathematical results. It concerns non-adiabatic spin flip. It reports what is known as Landau-Zener probability. And it is interesting to note that the derivation in modern books of the Landau-Zener probability follows closely that reported clearer by Majorana rather than that reported by Landau-Zener or in Stuckelberg. Well, about mathematical results, They concern the reduction of a system with arbitrary angular momentum to that of a spin 1/2 discovered only much later. And in particular, the introduction of a so-called Majorana sphere for representing the states of such a system, which is a generalization of what done later, 1948, by Nobel laureates Felix Bloch for only a special case known as a Bloch sphere. The representation with the Majorana sphere has proved particularly relevant, especially in recent years. Also, for example, in quantum computing, just to quote an example. Instead, what about physical results? What contained in the Majorana paper served, first of all, for example, for nuclear magnetic resonance done by Isaac Rabi, another Nobel laureate. Also for the Majorana-Brossel effect, the realization of Bose-Einstein condensation, another Nobel Prize in 2001, and so on, in many other places. Paper number 7 on relativistic theory of particles with arbitrary intrinsic angular momentum is no doubt the most important one by Majorana. Here he practically founded the theoretical particle physics based on variational principles and group theory methods just into the research. Equally certain, however, is the fact that this is Majorana's most complicated article. Just think of the fact, for example, that he took Pauli, and this student Firth, quite a few years, several years, to understand it as evidenced by their correspondence. Majorana discovered here the so-called infinite dimensional representation of the Lorentz group. They were only several years later rediscovered by Eugene Wigner. Thanks to the intervention by Amaldi, the paper was later rediscovered by Fradegin, another theoretician, in 1966. And from that moment on, a large number of works appeared dealing with that theory, including papers by Baut, Sudarshan, Dirac himself, till recent times, when Sagnotti in 2012 recognized that the paper anticipated both Reggie's idea and its eventual realization in the Veneziano amplitude, that is, in a sense, the string theory. The best known article during Majorana's life is, on the other hand, paper number 8 on nuclear theory, where he gave the first consistent theory of nuclei as composed by protons and neutrons. Why consistent? I say consistent. Why consistent? Well, when the news of Chadwick's discovery of the neutron reached Rome in March 1932, according to Amaldi, Sergej, etc., Majorana promptly elaborated his theory, his nuclear theory, which he discussed also with Fermi. Fermi soon realized the relevance of Majorana's results, so that he obviously urged him to publish the theory. Majorana, however, according to his hypercritical view, considered his work incomplete. This is not true, if we look at his personal notebooks. However, he refused to publish it. When several months later, in July, a paper by Heisenberg appeared reporting the first nuclear theory, first published nuclear theory, Fermi again urged Majorana to publish his theory, and again Majorana refused to do. noting that Heisenberg has already done everything, even too much. What did that mean? Well, according to Heisenberg theory, the most stable light nucleus should be deuterium, while it was well known that it was rather helium, the most stable one, that is alpha particles. This came from the fact that while in both theories the forces responsible for the nuclear binding were quantum mechanical exchange forces, Heisenberg considered the exchange of both position and charge of what we term now nucleons. Practically, he incorrectly imaged the neutron as a compound state of a proton and an electron, exchanging an electron when interacting with another proton, for example. Instead, Majorana correctly considered the neutron not as a compound object, but rather as a neutral proton, according to his own wording, so that it based nuclear binding just on the exchange of only position. And just this directly prevented the nuclear collapse at short distances, while predicted the stability of the alpha particles rather than deuterons. Fermi failed to convince Majorana to publish his work, but succeeded to convince him to go to Leipzig at the beginning of 1933 to work with Heisenberg. And Heisenberg finally managed to persuade Majorana to publish his correct theory, that is just paper number 8. Interesting enough, in all subsequent conferences and congresses, Heisenberg always emphasized Majorana's contribution rather than his own. Paper number 8 also contains two other remarkable things. You see here that is, first of all, the first application of the Thomas Fermi model to nuclei rather than to atoms, and then the anticipation of the Yukawa interaction potential. Paper number 9 is instead Majorana's best known paper now, today. It contains the famous Majorana neutrino hypothesis. It was originally aimed at providing a reformulation of the Dirac theory that was completely symmetric between electron and positron components. Starting again from a variational principle, Majorana succeeded to obtain a real wave equation, rather than complex one, which he properly quantized, also automatically obtaining a cancellation of some divergences, which were instead only artificially removed in the Dirac theory, as you probably know. Such a real equation allowed novel solutions for neutral particles, not limited to neutrinos. Indeed, Majorana particles are in general spin-1/2 particles that coincide with their antiparticles. Particles and antiparticles coincide. Again, a revolutionary idea, especially for those time after the success of the Dirac equation. Majorana neutrinos are responsible, if any, of the neutrinoless double beta decay, as envisaged by Mendel-Furry shortly after. But here the experimental research has not yet given a definite result. Also, I note here that the phenomenon of neutrino oscillation, which was suggested by Bruno Pontecorvo, another former member of the Fermi group in Rome, the phenomenon of neutrino oscillation firstly appeared as a neutrino-antineutrino oscillation rather than what is known as a flavor oscillation. Neutrino and neutrino oscillation are allowed only if neutrinos are Majorana particles, is also assumed in the first phenomenological theory of neutrino oscillation, 1969, by Grigor. Flavor oscillation were directly observed in 1998, but the experimental hunting of Majorana's neutrino still continues. But Majorana particles appear also in other fields, that is, for example, in supersymmetry, where they play a key role in the unification of the fundamental interactions in dark matter, and so on. Even here, the research continues. Also, they appear as Majorana fermions in condensed matter systems, for example, ferromagnetism, superconductivity, topological insulators, also in connection with the quantum computing, and so on. Well, finally, in the list of papers published by Majorana, a 10th paper is included that was published in 1942 by his friend Giovannino Gentile, although it was written in 1936 upon request of his uncle Giuseppe Nepomuceno. It is quite a peculiar paper on the value of statistical laws in physics and in social sciences, aimed at applying an approach to society within the framework of statistical physics, practically by reversing the economic paradigm just developed in those years in terms of a rather strict determinism, in analogy, for example, with celestial mechanics. Interestingly, it is the first paper, the very first paper on complex systems, where even this very term, complex system, appears for the first time in the literature. This program was later realized, Majorana was unknown, of course, for example, in the Bleche-Scholz model of option pricing, for which the two scholars received the Nobel Prize in the 70s. And among the other things, it served in 1997 to found a completely new discipline, that is econophysics. You see here Mantegna, Stanley, Eugene Stanley, the founders of econophysics. The paper has been studied also by sociologists, epistemologists, and so on. However, let us now return to physics. As I have already anticipated, what I have just briefly told is only a small part of what Majorana achieved. Unpublished notes account for thousands and thousands of pages now kept in Pisa, the Dome of Galilea. A significant part of these notes have been studied recently and even published in several books you see here. In order to give you an idea, just an idea, of what contained in such unpublished pages, I will now mention just a few examples of what you can find in their published notes. For example, at the end of the 20s, Majorana developed what was later known as the Pauli-Weisskopf theory of scalar electrodynamics. That is a consistent quantum field theory, even for particles without spin 1/2, as for the Dirac particles. As recalled by Weisskopf, it was a tremendous fun in working out something that at that time was quite unexpected, that one can get a pair creation and pair annihilation without a Dirac equation, also for particles without spin. Note, however, that the Majorana theory is also a bit more general than the Pauli-Weisskopf one, even in some applications. Majorana also anticipated in other pages the typical reasoning of Feynman quantum electrodynamics, where electromagnetic interaction between two bodies and two electrons, for example, is mediated by particle exchange. In Majorana notebook, we also find several generalizations of the Thomas Fermi model mentioned earlier, with a number of applications, ions, molecules, and so on. As I recalled above, a detailed study is performed of quasi-stationary states in nuclear physics, nuclear, not atomic physics. They were aimed at generalizing the Gamow model describing the nuclear alpha decay. Also, in some notes, Majorana provided a physical interpretation of quantum mechanics, which anticipated the Feynman approach in terms of path integrals. Here, the interesting thing is that this was done independently of the underlying mathematical formulation. Here we have other works on quantum electrodynamics, a subject much studied by Majorana, but I want to finally focus on a very interesting alternative theory of ferromagnetism. This follows just, this theory follows just the same guidelines of the Heisenberg theory of ferromagnetism of 1928. That is the framework of the statistical Ising model. Although Majorana considered the more general wave functions written in terms of Slater determinants in order to include from the beginning the constraints imposed by the Pauli exclusion principle. But interesting enough, the Majorana theory is different and clearer than the original Heisenberg one. For example, the partition function of the system is obtained by solving a differential equation rather than following a algebraic method as in Heisenberg. And Majorana went well beyond the usual Gaussian approximation with terms up in the series expansion up to order 10. Imagine. Of course, the theory successful in predicting a non-vanishing critical temperature, just as in Heisenberg one. But contrary to what happens in this, Majorana's theory also predicts that ferromagnetism develops only in systems in more than one dimension, thus anticipating a later key result by Rudolf Fires. Furthermore, we also find in the notebook several applications of the theory to different geometrical arrangements of the elementary magnets, etc., etc. Finally, let me say just a few more words about Majorana as a teacher rather than as a scientist. Indeed, Majorana did intend to teach theoretical physics. In 1932, he became a libero docente, something analogous to the English lecturer or German Privatdozent. And as discovered quite recently, in the subsequent years, he also proposed repeatedly several courses at the University of Rome. For example, mathematical methods of quantum mechanics was proposed in 1933, mathematical methods of atomic physics in 1935, and quantum electrodynamics in 1936. However, none of these courses was effectively delivered. this probably explains why testimonies like Amal, etc., forgot this. Now, if you have a look at the syllabuses of such courses, you easily realize why these courses were not taught. They were extremely advanced for those times, and actually in Italy, more or less just Fermi was able to take them. However, Majorana finally succeeded in teaching theoretical physics sometime later. Indeed, in 1937, a Nobel competition was opened in Italy for a chair in theoretical physics at the University of Palermo. And Majorana was among the applicants, including other renowned physicists, Giancarlo Vic, Giulio Racah, Giovanni Gentile, and others. The judging committee, chaired by Fermi, as soon as it took office, analyzed the papers presented by the applicants and immediately stopped its work by proposing to the Minister of Education to appoint Majorana as Professor of Theoretical Physics for his high and well-deserved repute in one of the Kingdom University, independently from the competition. After 2 days, the minister accepted his proposal, and Majorana obtained the chair of theoretical physics at the University of Naples. This is the second one in Italy, after Fermi's chair. He then moved to Naples, and in January 1938, he started the course, which immediately revealed itself as the most advanced one in Italy, even with respect to the Fermi course in Rome. In addition to quantum mechanics, Majorana, for example, also included some lectures on the theory of relativity. Note that this was the first time in Italy for a physics course. And, well, it was really a modern course on quantum mechanics, following more or less the same lines as in today's courses. Unfortunately, Majorana gave only 21 lectures since on March 25, Friday without lectures. He went to the Institute of Physics in Naples, leaving a folder with these lecture notes to one of his students, Gilda Senatore. Then he came back to his hotel, which he left in the late afternoon for probably embarking on the ferry to Palermo, and we have no more certain news about him. Let me finish with quoting once more Fermi, when he wrote to the Italian Prime Minister Mussolini in order to intensify searches. Able at the same time to develop audacious hypotheses and criticize acutely his work and that of others. Very skilled calculating man, a deep-rooted mathematician that never loses the very essence of the physical problem behind the veil of numbers and algorithms. Ettore Majorana has at the highest level that rare collection of ability which formed the theoretical physicist of very first rank. Indeed, in the few years during which his activity has been carried out until now, he has been able to outclass the attention of scholars from all over the world who recognize in his works the stamp of one of the greatest minds of our times and the promise of further conquests. Beyond the rhetoric used in this formal letter, I believe that the further conquests alluded here very well evidenced by the large number of Majorana terms, let me say this, that can be found into the literature: Majorana condition, Majorana electron, Majorana equation, Majorana, and etc. Well, here are some references if you are interested in learning more about Majorana. I conclude. Thank you for your attention.
Many thanks to you for this wonderful, very wide and in-depth presentation of the, not only the person, the scientist, but also of the interesting work of Majorana. I like so much this approach to history of physics, in which you are looking to the contents, you are looking to the way in which physics is developed through the person who have developed, to scientists. So many, many thanks a lot. I have a question. I perceive, but maybe I'm wrong, that a lot of the results of the way in which Majorana clarifies some concept were in their own lectures. So I ask you, how much you feel relevant lectures of Majorana?
According to what point of view? From a teaching point of view, a theoretical physics, or what? Because
from conceptual point of view, for what concerns the meaning of certain concepts, because it appeared to me that reading his own lectures, there are emerging some global vision of concept that are only formally expressed before.
Yes,
is it true?
I
don't know.
No, Marisa, this is completely true. It was, of course, he was not the only scholar who understood quantum mechanics, but if you read his lecture notes for the course, you realized indeed that he had a comprehensive view, starting from experiments, and then first passing from experiments to the old quantum theory. Old quantum theory was introduced in order to interpret experiments. For example, the Einstein experiments.
Yes.
For quantum effect and so on. Then he switched to a more mathematical description, or rather quantum mechanical description. Indeed, the theory of relativity was introduced just as a bridge between the two parts of the courses. If you compare, for example, with Heisenberg-Dirac, which are more or less contemporary, you indeed find a comprehensive view, but not limited to mathematics. If you read the Dirac book, or even in some sense the Heisenberg book, the Principle of Quantum Mechanics, you see mathematics has a very key role in explaining quantum mechanics. Well, mathematics has a key role also in Majorana presentation, but Majorana probably heard by Fermi a phenomenological approach, and then his lectures are full of this approach, although he also presented the general view according, for example, to Heisenberg Schrödinger, for example.
Okay, so I'm so sorry because we are a little bit late, and I don't know if there is some urgent question. Please do, otherwise I have to pass to the next speakers. Okay, so no urgent request, and I thank you one more for the wonderful contribution, and I introduce Matteo Leone. Matteo Leone is one of my best friends. I like a lot his work in history of physics, and also recently in physics education. He's another historian in the history of physics research who approach history of physics looking to physics inside. So Matteo Leone is full professor at the Department of Philosophy and Educational Science at University of Torino, where he is professor of fundamental and didactics of physics for the master degree in primary teacher education. For several years, he has been president of his degree course and director of the Physics Museum of the University in Torino. His research interests include the history of modern physics, the educational potential of the history of physics, and the mental representation of primary and old school children. So his wide perspective is very relevant for us. He has published in the main international journal of didactic and history of physics, such as American Journal of Physics, European Journal of Physics, Physics Education, Physics in Perspective, and Science Education. Recently, he published, he produced a monography concerning the Italian physicists appointed senators, politicians with relevant role in the government. And University Manual on the Teaching of Physics in Kindergarten and Primary School, published by Mondadori, a very well-known publisher in Italy. So I thank a lot Matteo for accepting to give us his invited talk on Pontecorvo and the detection of neutrino investigation. Please, Matteo, you have microphone.
Thank you, Marisa. I'll try to share the screen. I hope you can see the screen.
Yes, yes.
Okay. First of all, I would like to thank the organizing and the scientific committees, and above all, Marisa, for this kind invitation to this important conference. In this talk, I will discuss about Pontecorvo's early contribution to the detection of neutrinos. This is the outline of this talk. The most important thing to tell to you is that this work was carried out in collaboration with Professor Nadia Robotti from the University of Genova. And it is also important to present the main archival sources used for this research, which are the National Archives in Kew Garden, London, the Churchill Archives Centre in Cambridge, and the National Research Council of Canada Archives in Ottawa. And let's start with the silence of the neutrino. In which sense silence? Silent. For many years, as it is well known, neutrino had been a silent particle. For example, we have here a number of sentences told by prominent physicists. For example, Chadwick, the discoverer of the neutron in 1932, in 1933 at the Solvay conference, told that it is certain that the neutrino, if it exists, would be excessively hard to detect. And Alvarez in 1949 It is unfortunate that at the present time, there is no convincing experimental proof that neutrinos exist. And Reins, in his Nobel lecture in 1995, titled his lecture, "The Neutrino from Poltergeist to Particle." The first method that was attempted to detect neutrino since 1936 was the recoil method. That is the measurement of energy and momentum of the recoil nucleus and of all other particles emitted in a beta disintegration decay process. But the result of these experiments were that the energy and momentum are not conserved unless the neutrino is produced to carry away the missing momentum and energy. But this was an indirect method. That is, the recoil experiments were interpreted on the basis of the assumption that the law of conservation of energy and momentum hold in a single beta process. There was also another method that was attempted, namely by Chadwick in 1934 with Leah, the ionization method. And this method was attempted at the Cavendish laboratory in Cambridge with a continuous beta ray spectrum of radium E, that is bismuth 210, and the measurements of ionization with still-walled ionization chamber. So the device was a ionization chamber. This experiment led to negative result, no indication of any component other than the polonium gamma ray. It is of interest to consider the bearing of this negative result on the hypothesis of the neutral particle. The ionization produced by the neutral particle cannot exceed one ion pair in 150 kilometer path in air at NTP. And this negative results was confirmed by other experiments carried out by Namias with Geiger-Müller counters. And what is interesting about this experiment is that they were carried out in the Holborn tube station in London at a depth of about 30 meters underground in order to have a cosmic ray intensity small. This is, therefore, a first case of underground experiments on neutrinos. But once again, Namias obtained a negative result because a neutrino does not produce as many as one primary encounter in 300,000 kilometers of air at NTP. But about in the same time, in 1934, another method was suggested. And this was a direct method. This method was proposed by Bethe and Piles in the February 1934 in a letter to Nature. This method derived from the Fermi's theory of beta decay of December 1933. And in their letter, Bethe and Piles wrote that the possibility of creating neutrinos necessarily implies the existence of annihilation processes. The most interesting among them would be the following. A neutrino hits a nucleus and a positive or negative electron is created while the neutrino disappears and the charge of the nucleus changes by 1, as in the equation here in the left. This is one process which neutrino can certainly cause, told Bethe. But alas, certainly cause, but this is absolutely impossible to observed Bethe, because the cross-section for this reaction would be of the order of 10 to the elevated to the minus 44 square centimeter, and corresponding to a penetrating power of 10 to elevated to the 16 kilometer. That is about 1,000 light years of solid matter. And this, of course, was an element that led Bethe and most of the other researchers think that it was impossible to observe a particle so penetrating. So this was the neutrino was to be considered completely unobservable. Then let's see briefly to a first protagonist of this way of detecting neutrinos. That is Horace Richard Crane, which was a PhD in physics at Caltech in 1934 with a supervisor Charles Lauritsen, that was a very important physicist who had introduced the accelerator-based nuclear physics to Caltech. In the years 33 and 34, Crane worked with Lauritsen on the artificial disintegration of light elements with alpha deutons and proton bombardment. And from 1935 onwards, he moved from Caltech, from California, to the University of Michigan, where from 1937 to 1939, he attempted with Halpern to detect neutrinos by the recoil nuclei and beta in a cloud chamber. That is a method that we have seen above. And Crane and Halpern found by using gaseous compound as a source and a cloud chamber for observation of beta particles recoil, they found that the recoils producing a large number of droplets are associated with beta particles of low momentum as often as they are with beta particles of high momentum. And this is a cloud chamber photographs showing beta ray tracks of intermediate energy, showing cluster of droplets at the beginning points. This method, however, did not prove the existence of neutrino. And the interesting thing is that in an interview of Crane with Ashley and Stewart in 1990, Crane told to Stewart that was the main thing we did on neutrinos, so the experiment with the cloud chamber. In fact, the only thing. And then emphasize a thing, Crane, except that bag of salt experiment, which was on such a small scale, we really weren't expecting anything. And then he added, I think I dreamed up the idea that you would need some reaction where the product of the neutrino reaction would be separable from the mass of the material. That's what Davis' experiment did. That is the discoverer of the solar neutrinos. What is this bag of salt experiment that Crane talked about in 1919? This experiment was briefly discussed by Crane in a short article on Physical Review in 1939 titled An Attempt to Observe the Absorption of Neutrinos. In this paper, Crane suggested using an inverse beta process in the form of a reaction on a chlorine isotope, chlorine 35. Why chlorine 35? Essentially because of the low energy threshold of the reaction that led from chlorine 35 to sulfur 35, and then the ease to isolate the reaction product, that is sulfur 35, because an evidence of the production of an evidence of the existence of neutrino would be the production of sulfur. So it was important to isolate this product. The Crane's recipe is listed here. 1 millicurie of mesothorium, that is radium 228, whose neutrino have energies of 1.3 MeV, a bag containing just over 1 kilogram of cooking salt, really cooking salt, and 3 months of irradiation and sulfur extraction and activity measurements. What was the result of this experiment? Perhaps Crane, as he later told to Stewart, he did not expect anything. Anyway, no measurable activity was found. The source used by Crane yielded 30 millions of neutrinos, but only a cross-section as high as 10 to the minus 30 square centimeter could have been detected in a far greater cross-section than expected by Bethe piles. But Crane, in reality, was mainly interested in solar neutrinos, even if he used in his experiment the millicurium mesothorium. He was interested in solar neutrinos after having observed, on the basis of the recently developed Bethe theory of energy production in stars, that a star generates about 6% of its energy in the form of neutrinos. He took the view that it is of interest to know whether the neutrinos escape from the center of the sun without further collision with matter. And furthermore, if his bag of salt experiment was repeated again with a stronger source of mesothorium or radium, it could be possible, according to Crane, to determine whether an absorption mechanism like inverse beta process was great enough to prevent the escape of neutrinos from the sun. However, even if Crane was interested in the flux of solar neutrinos, he did not discuss his chlorine sulfur method as a possible way to detect solar neutrinos. In his paper, he implicitly referred to Bethe's theories of energy production in stars. Only in January in a review paper he drafted in 1948, Crane hinted at such a possibility. The energy spectrum of the neutrino produced in the sun, in particular in the CNO beta cycle, is not unfavorable for the inverse beta process. Yet, observed Crane in 1948, the use of the large neutrino flux from a chain reaction pile to test for the inverse beta decay process has been a subject of conversation among physicists since the advent of the pile, and it would be surprising if experiments of this sort were not going forward at the present time in one or more of the government laboratories. And Crane's guess was correct. We now know that since 1945, another Italian nuclear physicist who was working in a Canadian government laboratory as a part of a classified project had been thinking about detecting pile neutrinos through a method almost identical to that used by Crane, so with negative results. A few years earlier, his name was Bruno Pontecorvo. Bruno Pontecorvo, by early 1943 until 1949, participated in a secret government project in Canada, and in particular in Montreal and Chalk River, a project codenamed Tubalois, consisting mainly on working on the design of heavy water natural uranium reactor. This project involved mainly British physicists from Cambridge. In these photographs, we can see a number of physicists: Alban Cockcroft, Pontecorvo, Lawrence, and Nunn-May. It is interesting to see what Michael Perrin, deputy director of the Directorate of Tubalois, wrote in December 1942 to Sir Edward Appleton, the secretary of the Department of Scientific Industrial Research that in 1941 was given the responsibility of creating and managing the Directorate of Tubelois. And he wrote Wallace Akers, that was the director of the Directorate of Tubelois, pointed out that Auger and Plagiek had made a very strong case on the value of Pontecorvo, as we could not get British physicists of equal standing, we ought not object to taking on foreigners as the Italian Pontecorvo. So we have very interesting remarks on the value of Pontecorvo here. Value of Pontecorvo as of 1942. In this document from the National Archives, we see that Pontecorvo entered the Tubelois officially in January 1943. And in particular, at first in Montreal and later in Chalk River, in particular, was in charge, it was within the physics division headed by Auger. In particular, it was in charge of section 2, neutron density distribution in an heterogeneous media. One of the things that Pontecorvo did during his period in Chalk River was relatively disconnected from his work on the nuclear reactor. In particular, in May 1945, he drafted a written note on neutrinos, titled "On a Method for Detecting Free Neutrinos," which was issued in May 21st, 1945. Here you can see the cover of these documents and preserved at the National Archives in London. This note was coded PD141, where PD meant the National Research Council of Canada, in particular the Division of Atomic Energy in Chalk River. It is interesting to observe that because of the sensitive content of this note, it was classified only in 1964. And in this note, in the introduction section, Pontecorvo covered, for example, the recoil method for detecting neutrinos, the most significant experiments. Then he discussed, this was the focus, the core note, the inverse beta process method for detecting free neutrinos. He admits that the cross-section for such nuclear disintegration produced by neutrinos is expected to be extremely small, according to Fermi theory. However, according to Pontecorvo, the object of this note is to show that the experimental observation of an inverse beta process is not out of the questions, and to suggest a method which might make an experimental observation feasible. So it was not only theoretically possible, but also, according to Pontecorvo, experimentally possible. At first, Pontecorvo covered the energetic conditions for the inverse beta process. I have here highlighted a typo in this formula. What is the meaning of this method? He wrote, it is true that the actual disintegration, the actual emission of an electron, positive or negative, when the neutrino is absorbed, is not detectable in practice. However, the nucleus of charge Z-1 or Z+1, which is produced in the reaction, may be, and in general will be, radioactive, with a decay period which usually be known from our knowledge of the properties of artificial radio elements. Consequently, the radioactivity of the produced nucleus may be looked for and studied as an indication of the inverse beta process produced by neutrinos. The essential point is that the radioactive atoms produced by this inverse beta process have different chemical properties from the irradiated atoms. And it is important to extract from an irradiated volume of the order of cubic meters. So what are the conditions to be met? First, the material must be cheap because cubic meters are involved. Second, the lifetimes has to be of the order of several days because the long time involved in the chemical separation. Then the chemical separation must be simple. The energy of the beta transformation must be small, that is the mass of Z has to be close to the mass of Z plus or minus 1. And when all these conditions are considered, according to Pontecorvo, chlorine fulfills reasonably well the desired conditions according to this reaction. The neutrinos plus chlorine 35s that produce a positive electron plus sulfur 35 that in turn decay in chlorine 35 plus a negative electron with a lifetime of 87 days, an energy of the beta of 120 keV, and the chlorine should be in the form of carbon tetrachloride. According to Pontecorvo, the production of sulfur 35 would be observable if the intensity is is at least of 10 to the 70 neutrinos per second. And it is important that Pontecorvo remarks that such an extremely intense source does not go much beyond the present technical facilities. In fact, the Fermi pile of 2 kilowatt emitted an order of 10 to the 14 power neutrinos per second. In an endnote of this report, Pontecorvo observed also that the flux of neutrinos from the sun is quite considerable, and in acknowledge for this observation, Price, Dr. Price, another member of the tube alloys. However, according to Pontecorvo, the value of neutrinos expected from the sun is too low for an experiment of the type suggested. Summing up, Pontecorvo suggests a chlorine reaction on neutrino with a reaction of neutrinos on chlorine 35. A reaction that, if you remember, was exactly the reaction formerly suggested by Crane. It is interesting that Pontecorvo does not mention Crane's work on the detection of neutrinos with inverse beta process, but only those on the recoil method. Pontecorvo knew Crane's work, but he quotes only Crane's experiment on the recoil method. It is important to observe that the papers, both papers of Crane were published in the same journal, that is on physical review. Let's see also the second important internal note drafted by Pontecorvo, PD 205. But let's begin with a later recollection by Pontecorvo himself, who wrote in 1983, sometime in 1947 or 1948, I was passing through Zurich and had lunch with Preiswerk and Pauli. I told Pauli about my plans concerning the method. They very much liked the idea itself, and he noted that it is not clear whether the reactor neutrinos would sufficiently effectively initiate the reaction, but in his opinion, they apparently should. And also in a paper devoted to Pontecorvo, published in 1997, Fide Caro wrote that in 1947, Bruno traveled to Europe for the first time after the war. As we have checked this information through the documents preserved by the National Archives, and we discovered that actually the first Pontecorvo's journey in Europe occurred not in 1947, but in 1946. You can see the summary of Pontecorvo's journeys during wartime. In particular, it is highlighted the journey in London, Zurich, Italy, and return. And this trip is supported by these other documents. This letter by Cockcroft on left, the authorization from the Swiss legation on the right concerning Pontecorvo's journey to Zurich in 1946. We can also see from Pontecorvo's passport, which you can see here, that there are the visas about Pontecorvo's trips in Europe, in particular in Switzerland. During this trip to Europe, Bradbury was the successor of Oppenheimer at the Los Alamos National Laboratory, invited Pontecorvo to lecture on the fundamental problems of nuclear physics at the Los Alamos conference to be held in August 1946. Pontecorvo accepted the invitation, apologizing for the delay because, of course, he was in Europe. And he considered giving a short communication on the subject, discussion on some methods to detect the inverse beta process. So he was quite interested also in 1946, not only in 1945, with this method for detecting, experimental detecting neutrino during his Chalk River period event. The project of the Pontecorvo's participation in this conference eventually does not go through due to the approval of the Atomic Energy Act on August 1, 1946. 1 month later, however, Pontecorvo delivered a conference on the same subject, the Nuclear Physics Conference in Montreal. You can see the program of this conference, and on September 4, 1946, at 11:15 in the morning, he talked about the inverse beta process. And inverse beta process is just the title of the second note which he wrote in Chalk River, devoted to the method for detecting neutrinos, a method for detecting neutrinos emitted by a reactor. We have found in this publication of the United States government publications that this note, the PD205, was declassified by the AEC, Atomic Energy Commission, on October 8, 1948. That is several years before the previous notes, and it was declassified a few days before other notes submitted to the same conference above discussed. What are the difference between PD205 and PD141? In both notes, we find the introduction neutrino detection through recoil nuclei, the idea of focusing on processes produced by neutrinos after they have emitted in a beta decay through an inverse beta process. According to Pontecorvo, in both notes, the possibility of observing an inverse beta process is not out of questions. He discusses in both notes the conditions that make experimental observation feasible. He considers in both notes chlorine as a good candidate in the form of carbon tetrachloride. He thinks that several cube meters of carbon tetrachloride are required, but the source, if such a volume of carbon tetrachloride requires a neutrino source, which though extremely intense, does not go much beyond the present technical facilities, that is nuclear reactor, either the hot uranium metal extracted from a pile or the pile itself during operation. He also considered, in both notes, the sun as a possible but weak source of neutrinos. There is, however, an important difference between these two notes. In PD 205, Pontecorvo suggests another reaction for chlorine. He suggests using chlorine 37 that produce argon 37 that by K capture becomes chlorine 37. Why this change? Pontecorvo's new attention for chlorine 37 as opposed to the previous chlorine 35 is a matter of speculation. No reference to PD 141 is made in his second report and in his later publications, also many years after the end of the war. What is clear is that at some point it became aware that relatively few difficulties in extraction of argon might be expected if you compare with the separation of sulfurous out of chlorine. And when only chemical methods are possible, as is the case for separating sulfur 35, this is a difficult separation. On the contrary, the nucleus formed in the inverse beta process is a rare gas as argon. The separation can be obtained by physical methods. Furthermore, Pontecorvo's new choice might be caused by his discovering at some point between the two reports the favorable decay mode of argon 37 by K electron capture. We have started with the silence of neutrino. Let's finish with the voice of neutrino. Pontecorvo remained in Canada, in Chalk River, until 1948. In that year, after being accepted and offered by Cockcroft, obtained the British citizenship. In early 1949, he moved to United Kingdom to work in Harwell at the Atomic Energy Research Establishment on reactor design. But neutrino research was not over in his mind. He wrote to Amaldi in June 1949, "Here I will try to do the experiment on free neutrinos I told you about years ago, extraction of argon 37 from carbon tetrachloride irradiated in quantities of several cubic meters from neutrinos from a pile. The experience is terribly acrobatic, but perhaps it is worth trying, and we have solved many technical difficulties." In that year, in 1949, in the meantime, Luis Alvarez discussed the Pontecorvo's chlorine-argon reaction in a University of California report and gave a widespread visibility to the method. Alvarez supported the Pontecorvo's conclusion on both reactor and solar neutrinos by quantitatively showing the feasibility of the method for detecting reactor neutrinos and by briefly commenting on the negligibility of the expected effects of solar neutrinos. At the end of the 40s, there was a problem about the nature of neutrinos emitted in beta minus and beta plus decays. In a letter to Pontecorvo by Tarkovic in 1948, for example, he wrote, "The theoretician have not yet decided if there is a real difference between a neutrino and an antineutrino. In this case, I wonder if the pile, that is beta decays, which furnishes antineutrinos, can induce a process such as the reaction from chlorine 37 to argon 37, which really requires neutrinos." And this question was solved in the first half of 1950s, when awareness was gained that neutrinos produced in a fusion reaction as in the sun and antineutrinos produced by reactor and radioactive sources are not identical. And this was achieved through experimental confirmation that the reaction with antineutrinos actually occurred if reactor antineutrinos are used. This was proved by Rains and Cowan in 1956. But also achieved through the experimental disconfirmation that the reaction from chlorine 37 to argon 37 with a neutrino does not take place if the same reactor antineutrinos are employed. This is a case when negative experiments are very, very important. This was obtained by Davis in 1954. This outcome stimulated Davis to produce Pontecorvo's chlorine-argon reaction by solar neutrinos, because it was demonstrated that the reaction neutrinos was not were not suitable to use. It was not suitable to use this chlorine-argon reaction to detect them. This choice required, however, the capability of observing much lower fluxes of energetic neutrinos with respect to those available near a large reactor and a new theoretical framework on solar neutrinos. But the conditions were met only in the mid-60s, when the development of models about energy production in the sun offered encouraging prospects for solar neutrino detection, as indeed Davis told in his Nobel lecture in 2002. In 1951, I began working on a chemical experiment for detecting neutrinos using a method that was suggested by Pontecorvo in 1946, and that has many similar techniques. I eventually used a large quantity of another molecules, the perchloroethylene, 400,000 liters of these molecules. As it is written in the Advanced Information and the Nobel Prize, Davis was a true pioneer, and his successful mastering of the extraction of few atoms out of 10 to the 30 power gave birth to a new field of neutrino physics. So, a few concluding remarks. Davis was able to detect solar neutrinos, as we have seen. I obtained the Nobel Prize for this, through the chlorine-argon method, a method suggested by Pontecorvo in 1946. Yet, as we have seen, Pontecorvo in 1946 planned to detect by this method pile neutrinos, nuclear reactor neutrinos. And with insight, we know that piles emit antineutrinos, which are not detectable with the chlorine-argon method. Actually, Pontecorvo's 1945 and Crane's 1939 chlorine-sulfur method could detect pile antineutrinos. However, it was abandoned for experimental difficulties. So, a real labyrinth. A second conclusion: is this case study useful also in an educational context? There is a wide literature on the use of history of science in the classroom, showing that this use shapes and improves students' views and knowledge on the nature of the natural science. For example, concerning scientific argumentation and modeling, for example, Hodgson wrote that the neglect of scientific argumentation in the school science curriculum gives the impression that science is the unproblematic accumulation of data and theory. In consequence, students are often puzzled and may even be alarmed by reports of disagreements among scientists on matters of contemporary importance. The recent COVID pandemic comes to mind and suggests that perhaps bringing in the classroom case studies like Pontecorvo's one would be of benefit to students and to their families. Thank you.
Thank you to you, Matteo. We are very honored of your presence, because you are the highest level of academic historian in physics of Italy, and not only for Italy, in Italy. But I have to thank you also for this last reflection on the role of history of physics in classroom, and you attach my very sensitive point, which is, in fact, how can we develop argumentation in a student without only storytelling? So, to her, by an historian of the research in physics, history of physics, that not storytelling but argumentation is the center of the work, is my big satisfaction, amazing satisfaction. But I have to let you know that I appreciate a lot how you present us the points, the relevant points, put in evidence by means of documents. I appreciate the internal coherence of the path in the presenting the different steps and results. So what we are discussing here, and not only here, in many physics education research environment, is how to develop physics identity and how to be able to put in evidence the internal coherence that our discipline asks. So your contribution is maybe the only one of history of physics that I consider a lecture for physics for everybody, as you have planned to consider for some, not only COVID, but for some lectures in school. Then I appreciate, in addition, the attention to physics as ground process and to the role of order of magnitude and its relevance of the order of magnitude of the quantity to establish the role that they have in the framework of the theoretical aspect. So another point is the wide spectra of evidence supported by research questions. So you put in evidence research questions and the results and problems and so on. And this is, in my opinion, a great contribution, examples on how history of physics can contribute not only to the research in history of physics, as you are expert and high-level researcher, but also in physics education. I'd like to thank you also for mentioning Nadia Robotti, my best friend. I invite her to come here, but she is just preparing a long trip and talk in Dublin, so she cannot come. But I find in your style also her style of work, and I love both for your way of working. So many times, I'm sorry, I take the time for every question. Maybe there are some questions I will check. No question at the moment, but I have to inform you that no more than one, but a big number of people from Fundamental Frontier of Physics came here now for this talk. And this is another gain that we have in the framework of Fundamental Frontier of Physics, because never happens that physicists participate to our session, and now they not only accept and appreciate our contribution, but also taking part to the question. There is a question by
Adele.
No, another
question. Yes, wait, I can,
yes.
I don't know if Adele can unmute herself, so I cannot unmute her, I think.
Hear me?
Okay, so yes.
Yeah, can you? Oh, okay. I thank you very much, Matteo, for this great talk. I have a curiosity about why Pontecorvo did not quote Crane in his paper on physical review about Crane's proposal of the chlorine method. As you said that he knew about it. Do you think there is some particular reason for not quoting him?
I don't know. We don't know. We talked about this for many months, many years, but I don't understand why. It is difficult to think that he did not know this report, but it is a conjecture. we cannot be sure of this. Surely, by sure, we know that for Crane, this was not an important method. He proposed this method as something like a divertissement, but he really did not expect that with 1 kilogram of salt, it was possible to detect neutrinos by the inverse beta decay. But really, I don't know why Pontecorvo did not quote him. Perhaps one possibility is that he did not know this report. Another possibility is that he read it at the time, but he forgot this note. Simultaneous or almost simultaneous discovery are quite frequent in science and in physics in particular. For example, the Stark-Lo-Surdo discovery. This is not not so simultaneous because Crane's note dated to 1939, and the first Pontecorvo's note was from 1945. In the middle, there was the Second World War. Anyway, I don't know, really. I don't know what is the reason for this. I don't think that it was malicious. Anyway, in the only published, quoted by himself report on this method, that is the PD205, he changed the method. It did not cover anymore the reaction with chlorine 35, so this episode is forgotten. But anyway, because of the intricacies of the neutrino versus antineutrinos, neutrino reactors, neutrinos from the sun, the later developments makes this previous hidden suggestion by Pontecorvo much more interesting. But as for your specific question, I have no answer. I'm very sorry.
Thank you, Matteo. It was just a curiosity because, of course, I do not think it was malicious. Probably, yeah, it's true. He forgot because many things happened in the meantime.
So I thank you one more, Sergej. There are other questions?
Nope. I don't see any.
Thanking one more Matteo, I wanted to suggest to all historians who are here now to gain room in FFP environment, because I started to invite you. You have to start to gain room in this environment. And this is the way in which I am starting to introduce Adele Larana.
Marisa, thank you again for your kind invitation.
Thank you for coming. Thank you for your time and for the wonderful, wonderful presentation you offer us. You offer really intellectual satisfaction. Absolutely. Many thanks. Many thanks. And please, you are very powerful man in the field, and you have not to lose the room for history of physics, both in FFP, but also in teacher education in Italy and in the world. So please, Matteo, you have in your hand the future of the group.
Okay. Thank you.
So starting from this stimulation, I will introduce our young promise, Adele Larana. She is from University of Verona. Adele Larana completed her PhD in physics in 2007 in the field of gravitational waves, LISA project. After 2 years spent in CERN, 2010-2012, collaborating with Ugo Amaldi, she has been working in history of physics at La Sapienza University in Rome, at the Enrico Fermi Center, which is well known, I believe, and later at the University of California. Member of the executive board of the Italian Society of History of Physics and Astronomy. She is currently a research fellow in History and Didactics of Physics at the University of Verona. She has been focusing on 3 main research issues: the history of gravitational wave research, a study of Edoardo Amaldi archives at La Sapienza University, and a prosopography of Italian physicists at all times, currently being published by the Italian Physical Society. She is a research associate of ENFN in the Virgo group of Sapienza University of Rome, a member of LIGO Virgo collaboration. So she is involved also in the physics of the history she is studying. She received in 2020 the prize of Italian Physical Society for the science communication on this field. She is working now with the Nobel laureate Barry Barish on a scientific biography of Edoardo Amaldi to be published by Oxford University Press in 2023. So now I leave you to present your contribution in our FFP16. Please, Adele.
Thank you very much, Marisa. I just share the screen, and so just tell me if you can see my screen. Is it okay?
Yes, I see very well.
Okay. First of all, I thank very much the organizer for so kindly inviting me in this gathering of distinguished scholars, and Marisa Michelini, first of all, of course. And I will speak in some sense in continuity with Matteo, because I will speak of another phenomena presumed to be undetectable, unobservable, such that gravitational waves have been doubted about also by Einstein himself, about not only their detectability, but also about their existence. So there it is. I will speak about gravitational waves. As you all know, the big announcement of the first detection of gravitational waves occurred on February 11, 2016, about 100 years after Einstein's first prediction of gravitational waves from this propagating kind of solutions of his field equations of the theory of general relativity. So on the 11th of February 2016, there was a joint announcement of the first detection of a gravitational wave signal by David Reitz, director of LIGO from Washington, and at the same time from the French-Italian experiment Virgo, so from the spokesperson of that time, Fulvio Ricci, who was in Cascina, so where the French-Italian experiment is located. So I just wanted to show to you, just to enter the enthusiasm of that moment.
We are glad to announce that we detected for the first time gravitational waves.
And this was very long chasing of this achievement, and as the distinguished theoretical particle physicist Luciano Maiani says, it was a kind of chasing the infinity. Luciano Maiani was the president of INFN when the approval of the Virgo project was signed both by the Italian National Institute for Nuclear Physics and by the French Conseil National de la Recherche Scientifique, CNRS. So saying that this was the chasing of infinity has a particular meaning, of course. So here are the current experiments, long-based gravitational wave detectors in the world. Current, I mean, in 2016. Now, currently, we have another one, which is in Japan, Kagra, but at the time of the announcement, these were the big interferometric antennas, which were about to start their first observing runs. Virgo was late, and the first observation, this first detection, which was both announced by LIGO and Virgo, was really made by the two LIGOs, and Virgo was still under an maintenance upgrade phase, so it was not running. But in virtue of a collaboration signed by LIGO and Virgo in 2007, the discovery paper was signed by about 1,000 physicists of this LIGO-Virgo collaboration. So, of course, you can see immediately here a kind of asymmetry between the European part and the USA part. Maybe you cannot see it already, but you will see it while I'm speaking about this. There is an evident asymmetry because the USA have two detectors, while in Europe there is only one, and this has had at the time and still has a big influence because gravitational wave detection and analysis is very much funded on coincident analysis between more than one gravitational wave detector. So this is a timeline of what was happening. The first detection happened on September 14, 2015, was announced a few months later in February 2016. Only the LIGO were working at the time, and still LIGO observes new signals, the second and third of these binary black hole mergers. And finally, in August 2017, Virgo joins the so-called O2 run of LIGO. So finally, we have three interferometric antennas working in the world, and immediately comes an outstanding observation by the three of these antennas. This detection comes on August 17 with the first detection of coalescence of two neutron stars, so colliding neutron stars, and with the beautiful observation of a kilonova, the first time that a gravitational wave signal can be used to direct the electromagnetic telescopes to look at the sky and identify some new thing that has been seen. So after the detection by LIGO and Virgo, immediately tens of telescopes from the Earth, radio telescopes, optical telescopes, and from space pointed at the region, at the patch identified in space by Virgo and LIGO as the source of this gravitational wave signals, and identified a new source of electromagnetic radiation. So this has been named as the first multi-messenger observation. Of course, this is not really true. It's the first multi-messenger observation with gravitational waves, because the first multi-messenger happened in the with the supernova of 1987, when the SN 1987 was observed through extragalactic neutrinos. That was the first observation of extragalactic neutrinos. So once again, we can link to Matteo's talk. So the first neutrinos seen not from the sun, but from outside. So first cosmic neutrinos. And that was also the first time that this observation of neutrinos from the outside was at the same time with the electromagnetic observation by the telescopes. So this was the first multi-messenger, but of course here we have the O3 run, which started in April 2019 and ended in March 2020 with the ended before the term because of the pandemic. And what happened since the first O1 run of observations? This is just to give a picture of what is now, how many events of coalescing binary systems we have observed with LIGO and Virgo, and Kagera in the meantime joined at the end of O3, LIGO and Virgo. So the Japanese experiment joined. It has not still this high sensitivity. It's target sensitivity, but it joined in any case. And you can see there are about 90 events. You see here, each event is represented by 3 little points, little balls, because we have these blue are the black holes which collide and give, you see the arrow goes up, a black hole, a third, one black hole, they collide, they become one black hole. And the red are the binary neutron stars colliding and giving something that is a little bit between gray and blue, because it is uncertain what we are seeing. We just see luminous gases, and we do not know if in the inside there is a black hole or a star, or a star forming from the collision of 2 stars. So you see about 90 events have been seen up to now, and this means something very important I'm just giving the context of my research, because this large number of coalescing binary systems allowed a very accurate and reliable modeling of these kinds of signals, the so-called chirping signals, because it is a signal coming from a coalescing system which gives a gravitational wave which looks like a chirp, which is the bird's chirping signal, as something that grows in frequency and intensity with time. Well, this deeply affected data analysis and sources detectability, so that at present now the single detector observations are given credence. But this is not the case for still undetected kinds of transient signals. This is very transient signals. We are speaking about signals that can last tenths of seconds. And for example, supernovae have not been yet observed through gravitational wave signals. And so still we need coincident analysis of more than one detector for signals which have not a robust modeling, because they have not been detected before. And of course, this was not the case before the first detections. Before the first detection of these beautiful binary coalescing signals, we needed coincident analysis of at least two detectors. Why? Well, this is a typical problem which is also about concerns, for example, the large arrays of radio telescopes, making coincident analysis between an array of detectors to lower the noise, the local noise. While a gravitational wave should excite both detectors almost at the same time, of course, local noise affects locally each detector. And so as non-Gaussian events mimic very well gravitational wave bursts, it is necessary to cancel out this noise and dig out from the noise in which it is buried the signal which we are looking for. So the only possibility is to perform coincidences between different detectors if we do not have a robust, really robust model of what we are looking for buried inside noise. And this means, of course, coincident analysis is very useful also to pinpoint the sources in the sky. So, of course, the presence of 3 antennas or 4 antennas is very important also for well-modeled signals, because one can pinpoint through the coincident analysis where the gravitational wave signal is coming in the sky, and so give the correct information to the electromagnetic counterparts to pinpoint and point, which takes some hours in some cases to point, also because the Earth in the meantime goes round, and so to pinpoint with the telescopes. So as you see, the problem is of that asymmetry which we were looking at in the picture of 2 LIGOs and 1 Virgo in Europe, is something that has something that the community of gravitational wave physicists has addressed many times in the past. Being an historian embedded in the scientific community, I've been involved in these discussions, and so started many years ago an accurate research about why Europe developed only 1 long-based interferometer instead of 2. And if we can learn something from the history of European gravitational research that we can that can be useful from history for the 3rd generation of interferometers, which is now being planned as the Einstein telescope. Well, my research, historical research, analyzed a great amount of archival, previously unexplored sources, and many interviews to direct protagonists, because we are speaking of very recent history of the late 1970s and all through 1980s, when indeed there was the project of a network of antennas in Europe, and it was being seriously discussed. Well, let's see. Of course, you know, you all know that the first proposal of antennas to detect gravitational waves comes from Joe Weber, and his work contributed to develop in the world many similar experiments based on resonant bars. So this is the first generation of detectors. Then came a second generation, which was resonant bars, but cooled to cryogenic temperatures. And then came a big jump to the 3rd generation, a big jump from bars to interferometric antennas. This was truly a huge leap in scale. As you can see here, Explorer, which was the antenna from the Rome, the group, research group in Rome, and which was located at CERN in Geneva, It was dismantled in 2012, and it was brought close to Virgo. And this is Explorer compared to Virgo. This is not only a resizing of science of gravitational waves in terms of facilities, it's resizing a number of people involved and of fundings. It's a great leap in scale. Something very similar is happening now while we are looking towards the new generation, future generation Einstein telescope of interferometric detectors, which calls for a European collaboration, which calls for more countries collaborating together. So you can see how my historical research, which I started in 2015, has much to do with the current things, and has gained some interest, attracted some interest in the scientific community, because what is happening now, that the Einstein telescope has reached some important milestones, and we are looking toward the future. So this is a picture between of the status of the gravitational wave detection groups in the world. But let's focus on who was working not on bars, but on interferometric detectors, the new generation of detectors in the 80s and in Europe. Just look at Europe. You see, there are these 4 groups. 3 were concentrating on optical problems. They were expert in laser interferometry and optic matters. One was in Glasgow, UK. One was in Orsay, Paris, led by Alain Brier. The one was in Munich, and then went to Garching, led by Billing. And there was a 4th group, which was not working on the core business of interferometric detectors, but on a complementary issue, which was the suspension of the mirrors of the interferometer to lower the seismic noise. And this was the group in Italy, led by Alberto Giazzotto in Pisa. So these are the 3 groups that you can see. The most ancient, let's say, the most old ones were the one in Germany and in England, which started to work on bars already at the beginning of the 70s, and then turned to the future, to this challenge of developing interferometric antennas, so the future antennas, in the middle of the 70s. And then at the beginning of the 80s, Alain Brier, here in the middle, started a group in Orsay. He was an engineer, expert in metrology and in the field of optics and lasers. And so he started an activity in this sense in the 80s, so with some, and all the 3 optical groups, let's call them like that, had proposed in the early 80s their own antenna. You see, in England, 1984, then developed in 1986, and submitted also to the Science Engineering Research Council of UK, so the UK funding agency. Same thing for the German proposal in 1985. We are speaking about kilometric long baseline interferometers. There were these proposals already being discussed in some sense at a very initial level, of course. And also Brier had started an investigation of the seismic noise in a place in the south of Paris, Nancy, for possible French interferometric antenna. This is a very preliminary, of course, proposals. But what is very important is that the 3 groups started to collaborate together very early in the 80s to discuss a common strategy to create a European network. And they also submitted an application for European Twinning Grant for the European Economic Committee Stimulation Program, and obtained it. So this was the first step towards a formal European collaboration for gravitational wave research. And of course, an outsider was in some sense Alberto Giazzotto. He was not coming from optics, not the core business of interferometric detectors. He was coming from particle physics, so from big science physics. He had worked at CERN. And he started his interest in gravitational wave detection started in the early 80s, when he wanted to change his research and do something of fundamental physics in another field. So he starts something that he finds suitable for his group, which is working on seismic isolation. He looks at this problem in some sense, some kind of Galilean approach that at the time was not looked very much in depth from other groups in the world, also from the USA, but he looks at this field developing some kind of suspension to suspend the mirror or the interferometer, which surely would turn to be something very important. And his interest is attracted by some facts that happen in astronomy, in particular the growing population of pulsars, which are being observed by the Australian radio telescope led by Dick Manchester. Why he was so interested in pulsars? This is a key element of this story, because pulsars are continuous, continuous sources of gravitational waves. If a pulsar has some kind of asymmetry, just a little mountain, for example, or something that makes it not symmetric and it rotates very fast, it emits gravitational waves. And this is a continuous signal, it's not a transient. This means that a single detector can look for much time, for many repeated cycles, for months at this signal, and finally integrate over time. And being alone, being a single detector, can detect alone that kind of source. So this is his, in some sense, his interest in being independent by the destiny, the fate of other facilities in the world. So this is a little timeline. Glasgow and Garching starting together interferometric activity in the middle of the 70s, Orsay starting at the beginning of the 80s, Pisa, Adalberto Giazzotto a little bit later, and finally having these grants, the first European grant only obtained by the three optical groups which were collaborating since the beginning, and then a second grant in which there is also the Pisa group. Well, Adalberto Giazzotto and Alain-Brié met in Rome at the Marcel-Grossman meeting of 1985. They had never met before. As I said, Adalberto Giazzotto was a little bit an outsider, who was not of the gravitational wave world. He was not participating at that time very much inside the discussions at the international level with the other groups in the US and in Europe. But finally, they met each other in Rome, and of course, they immediately recognized the complementarity of their expertises, and so something starts to work. These are the, of course, at the Marcel-Grossman meeting in Rome, there were all the European groups represented. Here, Jean-Yves Vinet is the theoretical phenomenologist, physicist of the Orsay group, presenting his theory of recycling, an idea first launched by Drive and fully developed by him. And you see the group Glasgow presenting some improvements, and also the group from Garching, of course. But what is happening here? Well, you can see the Marcel-Grossman meeting is not a meeting on gravitational waves. This is one of the big aspects of these times. There is no specific conference on gravitational waves. Master Grossman meeting is a general conference on general relativity and gravitation, and calls together experimental and theoretical physicists. The community of gravitational wave physicists did not exist yet. It was a very small world made of few groups, made of very few people. It is not big science at the time. It is still bench-top experiment science. So you see things go on, and finally Giazzotto writes in 1986 to Brillié, saying it should be then very nice if our two groups could collaborate together in view of the common scientific interests and of the complementary knowledges. And of course, the objective, the purpose is reaching good sensitivity at low frequency, you can see. So this is, things are going on. Brillié, of course, is aware of the collaborations which are going on, not only in Europe, but also with the USA. You can see the letter by Grieber and Rainer Weiss to Brillié in 1986. They had met each other in a meeting to discuss the collaboration between Europe and US, because at the same time in the US, the LIGO project was taking shape more and more. And so there are some questions that are raised by Ian Corbett. At the time, Ian Corbett was director of the Rutherford Appleton Lab in Chiltern and played an important role in the discussions between the European groups of gravitational waves. He did not, in the following years, he became a big personality inside the British funding agency, but he was coming from big science, from particle physicists, and had a role in trying to coordinate the work of these four small groups at the European level. And so he suggested to form a European gravitational wave detecting working party. This was going on, and at this stage, on April 24, only the optical teams were involved. Nobody knew about Giazzotto, nor they knew about the collaboration that was being established between the PISA group and the French group. You see the questions raised by Ian Corbett about this collaboration, European collaboration to be established. How will you organize the collaboration? We envisage a single coordination and management committee for the whole project, comprising several antennae and many interferometers. Should this committee have financial authority delegated by the funding agencies, or should the various national groups contribute to the equipment and manpower under their own control? You see, these are questions that are still very important now for the Einstein telescope. But what was happening? What was happening was that Brillié and Giazzotto had already made a formal type of collaboration and had submitted in May 1987 already, so just a few days after Ian Corbett's letter to the optical teams, a joint proposal. It was the first proposal of Virgo, May 1987. It is in Italian. It is an urgent proposal, and it was not discussed by Brillié and by Giazzotto with the other groups, European groups, which were counting on a common strategy. So when the optical groups go to the first meeting of the working party, they communicate, the French communicate, inform the others, the Glasgow and Gotchin team, that they had just submitted a proposal to INFN, a joint French-Italian proposal. That is, of course, a kind of bomb in some sense, because it violates the strategy that these optical groups were trying to adopt to negotiate with the funding agencies in their own countries and with the European Economic Community committees. So of course, this is something that tells much about what is happening. And I analyzed this in detail, and I don't want to, of course, steal more time than is due, but you see what in the proposal of 1987, the first vehicle proposal, you can see what is written in Italian, and it is in Italian for one reason, because it was written with much urgency by the Italian group of Pisa in order to submit this proposal in time to be included in the next 5-year plan of INFN, which happened, of course. This was the case. And of course, Giazzotto needed an optical group among the Italian teams that he had in the meanwhile gathered. All the Italian teams, among which the group of Napoli, did not have any expertise in optics. So the French group was essential. And at the same time, in this way, the group by Alain Brier could acquire a more stable position in the negotiations with the optical groups that were very competitive, of course, in Glasgow and Garching. So you can see what is very much stressed inside this first proposal. We will try to be the first to explore the low frequencies. The Italian group has acquired an expertise in low frequency strategy, which is not comparable to any other in the world. The low frequency strategy aimed to be independent of the fate of the other interferometric designs and of the collaboration with other comparable experiments. So at the end, after many discussions and a few meetings in which finally Giazzotto was included as part of the gravitational wave detector party, a report by the groups is being prepared. And this report gives birth to EuroGrav, the collaboration for the European Gravitational Interferometric Detectors Network. And of course, this is what the report says. All the members of the collaboration will work towards establishing the best possible European network with the aim of establishing a gravitational astronomy, a true observatory of gravitational waves, something that now we are speaking again about making Einstein telescope. An array of 3 detectors in Europe would give the European groups the minimum independence necessary to enable Europe to maintain its leading position in the field. And 3 European detectors operating with an American array, built either simultaneously or subsidiarily, would become one of the most important astronomical instruments of the modern age. So you can see it must be a reasonable European goal to build 3 detectors, you see, regardless, because this would provide extremely useful scientific information on its own, regardless of what happens in the world, which means what happens in the USA with the LIGO projects. So what did go wrong in all this? Well, many things went wrong. Of course, what happened was, first of all, that the 3 detectors became 2, the 3, because the German and British made a single joint proposal at the end of the 80s. And so from 3 reduced already to 2 because of economical problems, because in the meantime, the big history was also intercepting the small community of gravitational waves with a great reduction in funds for research in the UK, but also with the fall of the wall in Berlin, which meant the need for reorganization of and unifying the institutions from West and East of Germany, which meant funding and people, and so no possibility of looking to very big projects, and also very ambitious and probably a chasing the infinite, as Luciano Maiani said. So here are the main things that I have not time to analyze, but scientific disagreements played a big role. In particular, the difference in approaches, scientific approaches of the French-Italian groups and the British-German groups, which had their own prototypes, while the French-Italian team did not have a prototype. And this was a matter still now of hot discussion looking at the past. Of course, there was this difficult balance between national ambitions and international collaboration, and the difficult transition from benchtop experiments to big science. And of course, there was the absence of a coordinated gravitational wave community. If you wish to know a little bit more about this history, of course, this is my paper. It's a long work with many sources, and everything is explained in much detail. So thank you for your attention, and sorry to be late.
Oh, many thanks, Adele. You are let us clarify an actual research story. So you are just presenting not only what happens in the physics of the actual research, but also internal aspect, the social problem inside, internal, external social problem, and difficulties that the researcher finds. So there is something which is not only physics, but also the perspective of the human challenge that sometimes scientists are living. And in this case, you are helping us to understand many things. And I ask Sergej if there are some comment or request.
Nope. I cannot see any at this time.
No one. So I wish you is very late, very long day. I am tired. I don't know why.
I understand. Yes, of course.
Nothing, but apparently to pay attention to the good contributions that we receive is demanding. So apparently, so I will thank you so much. I wish you all the best for your career, for your future, and please don't forget to let us know about the story of your recent study on come si chiama questo? Mamma mia.
Oh, I help you about, you mean of the book?
Amaldi.
Amaldi, yeah.
I forgot the name of Amaldi. This is the maximum.
This means a lot. You're very
We can sell of the story of the Italian physicist, but anyway. So it happens. So many thanks, Adele. It was very emotional, in emotion to follow you and to be involved in such a sort of interesting story of physicists working now on what happens.
It's very hot matter. Yes.
Absolutely. So
thank you so much.
So Sergej, I thanks a lot for your help and for being a moderator of the session. And I believe that we can close the session inviting people to come tomorrow at 2 o'clock. Okay?
Yes,
Many
I agree.
thanks to everybody.
Bye.
Bye.
Thanks again. Bye-bye.